Somewhere out there, in the silent vastness of space, a star pulses with terrifying intensity. It's invisible to the naked eye, hidden 50,000 light-years away in the constellation Sagittarius. Yet one day, in the final days of 2004, it screamed across the cosmos with such violent energy that its echo reached Earth and literally shook our planet's magnetic field. That star is SGR1806-20, and it is unlike anything we've ever encountered. But before we continue, subscribe to the channel so you don't miss out on any of these videos. On December 27th of that year, something extraordinary happened. In less than a tenth of a second, a burst of energy was released that outshone every recorded stellar event except the Big Bang itself. The power it radiated was equivalent to what our Sun emits over the span of 100,000 years, compressed into a sliver of time so small it was almost imperceptible. Space-based gamma-ray detectors, including those aboard satellites, were briefly blinded. Some were saturated, overwhelmed by the sheer intensity of the signal. On Earth, sensitive instruments detected a sudden jolt in our planet's upper atmosphere, an effect no solar flare had ever accomplished to that degree. But how? How could a distant object do this? To answer that, we need to understand what SGR1806-20 is at its core. It's classified as a magnetar, a type of neutron star. Now, neutron stars themselves are already the densest observable objects in the known universe. They are formed when massive stars, 8 times or more the mass of our Sun, reach the end of their lives and explode in a supernova. The core that remains collapses into a small, ultra-dense sphere. Picture this: all the mass of our Sun crushed into something barely 20 kilometers across. A single sugar cube of neutron star material would weigh 1 billion tons on Earth. But even that doesn't prepare you for what a magnetar is. A magnetar is a neutron star with a magnetic field 1,000 times stronger than that of a typical neutron star. To be precise, the magnetic field of SGR1806-20 is estimated to be on the order of 2 times 10 superscript 1 Gauss. Earth's magnetic field, by comparison, is about 0.5 Gauss. So we're talking about a difference of 15 orders of magnitude. In fact, SGR1806-20 has the most intense magnetic field ever detected in the universe. This magnetic strength is so formidable that, if one were located within a few thousand kilometers of Earth, it could erase every magnetic strip on every credit card, distort the atoms in your body, and even pull the electrons off metal surfaces. But even more fascinating is how this magnetic field is structured. It's not uniform or stable. It's dynamic, twisted, coiled like a spring under unimaginable tension. Theoretically, such magnetars are born in supernovae under very specific conditions. As the core of the progenitor star collapses, it spins rapidly, hundreds of times per second, and this extreme rotation amplifies the magnetic field through a dynamo process. What you get is a cosmic engine wound tighter than anything we can fathom. These magnetic fields aren't just passive features. They affect everything about the magnetar. They influence its emissions, its temperature, even its crust, which is under constant stress. The intense magnetism cracks the solid surface, much like tectonic plates on Earth cause earthquakes. But in this case, these are called magnetic quakes, or starquakes. These events can twist the magnetic field even further, and in rare cases, release a massive explosion of energy. That's what scientists believe happened on December 27, 2004, with SGR1806-20. The energy released wasn't from the core exploding or the star dying. It was from its magnetic field snapping. In an instant, the tension that had built up over perhaps centuries gave way, releasing a titanic wave of gamma rays and X-rays. The flare was so powerful, it caused a brief compression of Earth's magnetic field, from 50,000 light-years away. Imagine a flare so strong that it traveled across half the galaxy, and still had enough energy to punch our planet's atmosphere. It almost defies logic. How could something so small, so far away, do something so incomprehensibly powerful? When SGR1806-20 unleashed its record-breaking flare, it compressed an entire cosmic lifetime's worth of energy into a blink. In just 0.1 seconds, it released more energy than the Sun will emit in 100,000 years. That's not a metaphor. It's a measurable fact, confirmed by satellites orbiting Earth and by observatories around the world. But how does such an event even occur? What mechanism could possibly allow such an astronomical energy release to happen so fast? To begin with, we have to understand the difference in energy output between normal stars and magnetars. The Sun, for all its might and brilliance, is a relatively gentle fusion reactor. Every second, it converts about 4 million tons of mass into energy through nuclear fusion, radiating that power outward in the form of light, heat, and solar wind. Over the course of 100,000 years, that adds up to an almost unimaginable amount of energy, roughly 10 superscript 3 ergs. Now consider that SGR 1806-20 discharged nearly 10 ergs in a tenth of a second. That's 1,000,000 trillion times more powerful than any nuclear explosion ever set off by humans. And it's not even the total energy stored in the magnetar, it's just the energy that happened to be released in that particular flare. This was not the death of a star, not the end of its life, but a sudden magnetic convulsion, a cosmic sneeze, if you will, that still dwarfed everything we know. The mechanism behind this terrifying release lies in the concept of magnetic reconnection and crustal failure. Imagine the magnetar's magnetic field as a bundle of tightly wound rubber bands, stretched to their absolute limit. Over time, stress builds up in the outer crust of the star, the solid, rigid layer that resists the immense pull of gravity, and the chaos of magnetism churning beneath it. Eventually, something has to give. At some critical point, the magnetic tension becomes too great. The crust fractures, possibly in multiple locations, and a starquake occurs. This rupture releases stored magnetic energy, which is converted into heat and radiation. The twisted field lines snap and reconnect, much like solar flares on the Sun but on a scale that's almost mythological. And when they do, they accelerate particles to near light speeds, generating an intense, focused burst of high-energy photons, gamma rays and X-rays. These particles and rays are expelled from the magnetar at nearly the speed of light, radiating outward in a beam. The burst is so focused and rapid that, by the time it reaches Earth, it arrives not as a diffuse glow, but as a blinding pulse that can overwhelm instruments. Some satellites that were monitoring gamma ray bursts at the time were momentarily rendered inoperable by the overload. That's how energetic it was. Interestingly, while the total energy output was astonishing, the event was extremely short-lived. Only a fraction of the flare was observable, and the rest of the energy may have been absorbed or spread out into space. Still, it was enough to compress the Earth's ionosphere, cause radio blackouts, and confuse astronomers across the globe. But this isn't a typical supernova or gamma ray burst from a collapsing black hole. This was the equivalent of a magnetic heartbeat, a sudden release of pent-up energy from a living, breathing neutron star. The power source wasn't gravity or fusion, but magnetism, on a scale we can barely comprehend. And the most haunting part: this might not even be the limit. If another magnetic fracture were to occur under even more extreme conditions, we could be facing a burst even stronger. SGR 1806-20 has shown us that the universe has far more violent extremes than we've imagined, and that energy, when twisted and stored in the fabric of space itself, can be unleashed in ways that rewrite our understanding of physics. A magnetar is one of the most bizarre and extreme types of stellar objects in the known universe. It's a neutron star, but not just any neutron star. It's a neutron star taken to its most violent and magnetic limit, a remnant so dense, so energetic, and so alien that it almost doesn't seem real. To fully appreciate why SGR 1806-20 is considered one of the most extreme magnetars ever discovered, we need to go back to the birth of these terrifying objects and unpack what makes them so fundamentally unique. When a massive star, at least 8 times the mass of our Sun, exhausts its nuclear fuel, it dies in a spectacular explosion known as a supernova. The outer layers are blasted into space, but the core collapses under its own gravity. If the star isn't massive enough to form a black hole, the result is a neutron star, an object so dense that a single teaspoon of its material would weigh around 1 billion tons. A neutron star is essentially a giant atomic nucleus, held together by gravity and governed by quantum physics. It spins rapidly, sometimes hundreds of times per second, and generates magnetic fields far stronger than anything we can replicate on Earth. But not all neutron stars are created equal. A very small percentage, fewer than 1 in 10, become magnetars. These are neutron stars with magnetic fields 1,000 times stronger than a typical neutron star, reaching up to 10^1 Gauss. For context, Earth's magnetic field is about 0.5 Gauss. A refrigerator magnet is roughly 50 Gauss. The strongest MRI machines are about 60,000 Gauss. Magnetars laugh at those numbers. Their magnetic fields are so intense that they could strip the electrons off atoms from hundreds of kilometers away. In fact, if a magnetar were brought within half the distance from the Earth to the Moon, it could literally destroy all electronic data on the planet, and possibly even tear the molecules in your body apart. So how do they get so magnetic? The leading theory involves a dynamo mechanism that occurs during the star's collapse. If the core is spinning rapidly enough, on the order of 1,000 revolutions per second, the motion amplifies the magnetic field, similar to how spinning coils generate electricity in a generator. But in this case, the generator is a collapsing star, and the coils are charged particles in a boiling sea of neutron-rich matter. This leads to the magnetic field winding up tighter and tighter, growing until it reaches insane intensities. After only a few thousand years, the spin slows down and the magnetic field weakens, which is why magnetars are thought to be relatively young on cosmic timescales, typically under 10,000 years old. Now, among these already rare and terrifying objects stands SGR1806-20, a magnetar that seems to push every known limit. SGR stands for soft gamma repeater, which refers to a type of magnetar known for releasing frequent bursts of low-energy gamma rays and X-rays. These bursts usually occur when the magnetic field distorts the star's crust, causing it to crack and snap back into place, a magnetic quake or starquake. SGR1806-20 has been on astronomers' radar for some time due to its erratic behavior and unusual energy signatures, but on December 27, 2004, it made history by releasing the brightest flash of energy ever detected from beyond our solar system. In that moment, SGR1806-20 didn't just act like a magnetar, it transcended what scientists thought magnetars were capable of. The gamma ray burst it released was so powerful that it saturated detectors on multiple satellites, including NASA's RESI, ESA's Integral, and even affected instruments not designed to observe gamma rays at all. The pulse was so intense that it briefly became the brightest source of gamma radiation in Earth's sky, second only to the Sun, and for a fleeting moment, it outshone the full moon in gamma wavelengths, despite being halfway across the Milky Way galaxy. SGR1806-20 is also unusually massive and highly magnetized, even for a magnetar. Located about 50,000 light-years from Earth in the constellation Sagittarius, it resides in a dense star-forming region known as the CL1806-20 cluster star. This region is home to several other massive stars and exotic objects, which makes it a kind of astrophysical laboratory. But even in that cosmic crowd, SGR1806-20 stands out as a true anomaly. Its surface temperature is estimated to be around 2 million Kelvin, and it's believed to emit an enormous amount of energy even when it's not flaring. But what truly sets it apart is the strength and complexity of its magnetic field. While most magnetars exhibit magnetic fields of about 10^1 to 10^1 Gauss, SGR1806-20 is likely on the upper edge of that range, possibly exceeding 2 times 10^1 Gauss, making it a serious contender for the strongest magnetic object in the known universe. Moreover, SGR1806-20 has a spin period of around 7.5 seconds, which is relatively slow for a neutron star. Most young neutron stars spin multiple times per second. But for a magnetar, this is expected. Its ultra-powerful magnetic field acts like a cosmic brake, bleeding off rotational energy extremely efficiently and slowing it down quickly. This also suggests that SGR1806-20 may be relatively young, likely less than 10,000 years old, and still active in its most energetic stage. One of the most terrifying aspects of this magnetar is the sheer unpredictability of its outbursts. The 2004 flare was not preceded by any warning signs visible from Earth. There were no rumblings or long-term changes in behavior that would have suggested it was about to explode in such a spectacular way. It just happened. Which leads scientists to wonder, how many other magnetars are out there, lying dormant, waiting to release their fury? And that's part of what makes SGR 1806-20 so extreme. Not just its numbers, the magnetic field strength, the energy output, the size of the flare, but its implications. It showed us that the universe can hide weapons of unimaginable power in plain sight. It taught us that even a neutron star, only a few dozen kilometers wide, can rival the explosive power of supernovae, and outshine an entire galaxy, for a moment. And perhaps most disturbingly, it proved that distance offers no guaranteed safety. If a flare like that had occurred just a few hundred light-years closer, Earth could have experienced devastating consequences, potentially catastrophic for satellites, power grids, and even the biosphere itself. We'll explore that possibility in more detail later, but for now, it's enough to recognize that SGR 1806-20 isn't just extreme. It's a reminder of the raw, unpredictable violence the cosmos is capable of. And we only noticed it because, for a tenth of a second, it screamed across space with such power that we had no choice but to listen. Magnetar flares, like the infamous eruption from SGR 1806-20, are often mentioned in the same breath as gamma-ray bursts, and for good reason. Both are some of the most energetic phenomena in the universe, releasing vast quantities of high-energy gamma radiation across enormous cosmic distances. But despite their surface similarities, magnetar flares and gamma-ray bursts, GRBs, are fundamentally different beasts in both origin and scale. Comparing them is like comparing a nuclear bomb to the birth of a galaxy. Each is violent, but one stems from internal frustration, and the other from cataclysmic collapse. To understand the distinction, we have to first examine what a gamma-ray burst is. GRBs come in two main types, long-duration and short-duration bursts. Long-duration GRBs typically last more than 2 seconds and are associated with the collapse of massive stars into black holes, so-called collapsars. These are supernova explosions on steroids, where a star dozens of times more massive than our Sun collapses under its own gravity. Instead of stabilizing as a neutron star, the core continues collapsing into a black hole. In the process, it creates powerful jets that shoot out at nearly the speed of light, bursting through the star's outer layers and emitting gamma rays as they escape. Short-duration GRBs, on the other hand, typically last less than 2 seconds and are thought to result from the merger of two neutron stars, or a neutron star and a black hole. These collisions are equally dramatic, releasing massive energy bursts in the form of tightly collimated jets of gamma radiation and often accompanied by gravitational waves, ripples in spacetime itself. Now here's where magnetar flares come in. Although they too emit gamma rays, they are not classified as gamma-ray bursts in the traditional sense. Instead, they are known as soft gamma repeater (SGR) flares or giant magnetar flares. And while they can be incredibly intense, SGR 1806-20's 2004 flare being the perfect example, their nature is fundamentally different. First and foremost, origin is key. Gamma-ray bursts are terminal events. They mark the end of a star's life, often resulting in a black hole. Magnetar flares, in contrast, are non-terminal. The magnetar survives. These flares are the result of magnetic instabilities within the star's crust or magnetic field, akin to a star quake or a magnetic eruption. No core collapse, no black hole, just an overwhelming release of stored magnetic energy. Then there's duration and structure. Gamma-ray bursts, especially the long ones, often exhibit a complex light curve that can last from a few seconds to several minutes, sometimes followed by an afterglow. In X-ray, optical, and radio wavelengths that can persist for days or even weeks. Magnetar flares, by contrast, tend to have a very sharp initial spike, lasting milliseconds to a fraction of a second, followed by a decaying tail that can last for minutes, often modulated by the star's rotation. SGR 1806-20's flare, for example, had a blinding initial burst that lasted about 0.2 seconds, so powerful that it saturated gamma ray detectors on multiple satellites. This was followed by a modulated tail lasting over 6 minutes, corresponding to the rotation period of the magnetar, which spins roughly every 7.5 seconds. In that tail, we saw pulsed emission that confirmed the burst originated from a rotating, magnetic neutron star. In terms of energy, magnetar flares and GRBs overlap but also diverge. A typical giant magnetar flare can release between 10 to 10 ergs of energy in gamma rays. The 2004 flare from SGR1806-20 was on the high end, estimated at around 10 ergs. Meanwhile, long-duration GRBs can release up to 10 superscript 1 to 10 superscript 3 ergs, though this is often collimated into narrow jets. If you were outside the jet's path, you might not even see the burst at all. In contrast, magnetar flares tend to be more isotropic, not focused into narrow beams but rather radiating in broader, less focused directions. Another important distinction lies in frequency and detectability. Magnetar flares, especially giant ones like that from SGR1806-20, are rare, but they happen within galaxies like ours. We've observed 3 major giant magnetar flares in the past few decades, from SGR0526, 66 in 1979, SGR 1900+14 in 1998, and SGR 1806-20 in 2004. Meanwhile, GRBs occur frequently on cosmic scales, detected roughly once per day across the entire observable universe, but usually very far away, in galaxies billions of light-years from Earth. This means that, paradoxically, a magnetar flare, although lower in total energy, is more dangerous to Earth if it happens nearby, because of its proximity and wide-angle emission. The 2004 flare from SGR 1806-20 was so far away, about 50,000 light-years, that it only caused minor disturbances to Earth's upper atmosphere. But if something like that occurred within, say, a few dozen light-years, the consequences could be catastrophic. It could strip the ozone layer, fry satellites, and cause mass extinctions, not because it's more energetic than a GRB, but because it's close. There's also the intriguing notion that some short gamma-ray bursts might actually be misidentified giant magnetar flares occurring in other galaxies. In fact, there has been serious scientific discussion about whether some distant, short-duration GRBs are not neutron star mergers at all, but rather extragalactic magnetar flares beaming directly at us. The energy profiles of some short GRBs have pulse structures and spectral features similar to magnetar bursts. If that's the case, we might be underestimating how common and powerful magnetar eruptions truly are. This leads us into the speculative but fascinating territory of fast radio bursts, FRBs, which we'll explore later. But even now, it's clear that magnetars could account for more than just dramatic gamma flares. They might be responsible for some of the most mysterious signals in the cosmos. So, while gamma-ray bursts are cosmic death knells, magnetar flares like SGR 1806-20 are more like cosmic tantrums, sudden, ferocious, but survivable outbursts from stars that are very much still alive. They differ in origin, duration, directionality, and frequency, but they converge in one critical area. They are both warnings of the raw and chaotic power of the universe. One comes from collapse, the other from instability. Both come from regions where matter is so dense and physics so twisted that our understanding teeters on the edge of science and the unknown. In that liminal space, where magnetic fields tear crusts apart and gamma rays pierce the fabric of space, we find SGR 1806-20. A magnetar whose flare was not a gamma-ray burst, but was certainly loud enough to echo across the galaxy like one. At the heart of a magnetar flare like the one observed from SGR 1806-20 lies a truly alien set of internal processes, ones that defy our earthly intuition. This isn't a simple volcanic eruption or a solar flare scaled up a bit. It's something far more violent and exotic. To truly grasp the anatomy of such an event, we must dive into the very bones of a magnetar, down into the ultra-dense crust and the twisted magnetic heart of this cosmic monster. A magnetar, first of all, is a type of neutron star, what's left after a massive star collapses under its own gravity. Its matter is so compressed that atoms break down into neutrons, forming a sphere just 20 to 25 kilometers across, yet heavier than our Sun. But a magnetar is a rare breed among neutron stars, born spinning rapidly and carrying with it a magnetic field a quadrillion times stronger than Earth's, sometimes exceeding 10 superscript 1 Gauss. This magnetic pressure is so intense, so outrageously beyond anything we can produce or experience on Earth, that it begins to reshape the star itself. And that's where the danger begins, because this internal magnetic pressure is not static. It's constantly shifting, twisting, and evolving. Imagine a steel ball whose magnetic fields are so strong they're trying to rip the ball apart from the inside, constantly pushing and distorting the material it's made of. The internal structure of a magnetar has three main components relevant to its flare mechanism. 1. The solid crust, an iron-rich crystalline shell just a kilometer thick. 2. The fluid neutron-rich core, a dense sea of degenerate nuclear matter. 3. The magnetic field, incredibly strong and largely hidden within, though it extends outward far into space. Now here's where things get volatile. Over time, the internal magnetic field of a magnetar begins to evolve and shift. This isn't a smooth process. It's chaotic and unpredictable. Because the crust of the magnetar is solid while the core is fluid, tensions begin to build, especially where the magnetic field lines become tangled or distorted. These tangled fields exert tremendous shear stresses on the crust, warping and twisting it like a stress rubber band just before it snaps. Eventually, the magnetic stress becomes too great, and the crust cracks in a seismic event called a magnetic star quake. But unlike Earth's tectonic earthquakes, this quake is driven by magnetic forces rather than mechanical ones. When the crust gives way, the magnetic field lines suddenly reconfigure, they untangle, in a violent release of stored energy. This is the core of the flare mechanism. When SGR1806-20 let loose its flare in December 2004, what happened was likely this. A portion of the magnetar's crust experienced a sudden, catastrophic failure due to the accumulated magnetic stress. The cracking of the crust allowed the tightly twisted magnetic field lines to violently snap into a new configuration, an event analogous to a solar flare but on a cosmic scale. This magnetic reconnection, where magnetic field lines snap and reconnect, converts massive amounts of magnetic energy into heat, particle acceleration, and crucially, gamma-ray radiation. It's similar in principle to what happens in solar flares, but the magnitude is orders of magnitude greater. In a solar flare, a few billion tons of plasma are hurled into space. In a magnetar flare, you're talking about a release of 10 ergs, more energy in a tenth of a second than the Sun produces in 100,000 years. But how is that energy released? As the magnetic field rearranges, it launches a fireball of ultra-energetic particles and photons, predominantly gamma rays and X-rays. This fireball rapidly expands away from the magnetar at nearly the speed of light. The initial spike, lasting milliseconds to fractions of a second, is a blast of hard gamma rays, so bright that it can saturate detectors and cast shadows across spacecraft shielding. This is the first signal received by Earth-based and space-based telescopes. Following that, the magnetosphere, the space surrounding the magnetar threaded with magnetic field lines, becomes highly energized. As this magnetosphere stabilizes after the quake, it traps high-energy particles, which then cools slowly, releasing pulsed X-ray emission modulated by the star's rotation. This is what created the 7.5-second pulses in the tail of the SGR1806-20 flare, continuing for over 5 minutes after the initial spike. Another fascinating piece is that the crust cracking likely sends seismic waves through the entire star, possibly exciting torsional oscillations, vibrations in the star's outer layers. In 2004, astronomers detected quasi-periodic oscillations (QPOs) in the flare's X-ray tail. These are believed to be literal ringing of the magnetar after the quake, like a bell that's just been struck. These QPOs may offer direct observational insight into the internal composition of neutron stars, something impossible to replicate in any lab. Interestingly, many researchers believe the magnetic field itself regenerates over time, fueled by complex processes in the fluid core. This means that even after a flare, a magnetar is not spent. It may build up stress again and erupt in another giant flare centuries, or just decades, later. There's still intense debate in the astrophysics community about whether crustal fractures alone account for these giant flares, or if deeper interactions in the core's superconducting fluid also contribute. Some models suggest that global magnetic instabilities may emerge when certain configurations of the core field become unstable, triggering not just a crustal quake, but a whole star rearrangement. And that's part of what makes magnetars, and SGR1806-20 in particular, so terrifyingly unpredictable. These flares are not periodic. They are spontaneous, triggered by hidden stresses deep within objects that we still barely understand. We can't predict when they'll go off, or how powerful they'll be. All we know is that when they do flare, the result is a cosmic detonation of pure magnetic rage. So, in essence, the internal process of a magnetar flare like that of SGR1806-20 is driven by decades or centuries of hidden magnetic stress, culminating in a sudden, catastrophic crustal rupture, a magnetic field reconfiguration, and a gamma-ray blast visible across the galaxy. It is a beautiful, terrifying process, a testament to the violent energy packed into these dense, spinning corpses of dead stars. The eruption from SGR1806-20 in December 2004 was one of the most energetic events ever witnessed in our galaxy, rivaling the brightness of the full moon in gamma rays and momentarily outshining everything else in the sky, except that this brilliance was invisible to the naked eye. Despite its astonishing power, releasing more energy in 0.1 seconds than our sun emits in 100,000 years, it didn't harm Earth or leave a noticeable mark on our everyday lives. But why? The answer lies in three crucial factors: distance, directionality, and atmospheric shielding. First, and most important, is distance. SGR1806-20 is located in the constellation Sagittarius, approximately 50,000 light-years away in the galactic plane, near the center of the Milky Way. To grasp how far that is, light, traveling at 299,792 kilometers per second, took 50,000 years just to reach us from that event. That's half the diameter of our galaxy. Even for an explosion of such titanic magnitude, this distance allowed the radiation to diffuse significantly before it ever reached Earth. The energy, though enormous at its source, was spread out over a vast cosmic volume, reducing the intensity that actually arrived here. Had the flare occurred just a few hundred light-years away, Earth could have faced serious consequences. If it were within 10 light-years, we might have seen atmospheric damage, ozone layer depletion, or even global ecological effects. But 50,000 light-years? That's like being on the opposite end of a football stadium from a camera flash, blinding at the source, barely a glimmer where you stand. Next is directionality. Unlike gamma-ray bursts from collapsing stars, which are often highly collimated into narrow beams, magnetar flares tend to emit their energy more spherically or broadly. However, there's still some degree of anisotropy, meaning some directions get more radiation than others. The beam or radiation pulse from SGR1806-20 was not pointed directly at Earth in a tightly focused jet. If it had been, we might have recorded a far more intense impact, perhaps even a measurable drop in atmospheric ozone or widespread satellite disruption. Instead, we caught the flare more off-axis, receiving a powerful but survivable dose. Think of it like standing near, but not directly in front of, a fire hose spray. You get wet, but not blasted off your feet. Then comes Earth's own atmospheric shielding, one of our most reliable and unsung defenders. Our planet's thick atmosphere, especially the upper layers like the ionosphere and stratosphere, acts as a sponge for high-energy radiation. Gamma rays and X-rays don't reach the ground. They are absorbed and scattered by atmospheric molecules high above us. While the December 27, 2004, flare did cause noticeable disturbances in the ionosphere, temporarily altering its electron density and even disrupting some radio communication systems on the sunlit side of Earth, these effects were short-lived and relatively minor. Satellites like RESI, Integral, SWIFT, and others were overwhelmed by the brightness of the initial spike, with many detectors saturated for fractions of a second. Even Earth's magnetic field experienced a brief ripple. Yet these were hiccups compared to the apocalyptic scenarios that might unfold if such an event occurred within our cosmic backyard. So although SGR 1806-20's flare was record-breaking in luminosity and energy output, space diluted it, Earth's position spared it, and our atmosphere defended it. It's also worth noting that while the event didn't damage human health or infrastructure, it was a cosmic wake-up call. The event highlighted just how vulnerable our modern world is to space weather, especially in an age where satellites, GPS systems, and high-frequency radio waves play critical roles in daily life. A closer or more focused flare could potentially wreak havoc on orbital electronics, communications networks, and even power grids, much like solar storms have been known to do, only far more abruptly and violently. Furthermore, this event showed scientists just how sensitive our instruments are, and how connected we are to cosmic activity even from across the galaxy. In fact, some early warning nuclear monitoring satellites, designed to detect gamma radiation from potential nuclear explosions on Earth, were among the first to register the spike, initially alarming defense officials before being quickly traced to a celestial source. In essence, Earth dodged a bullet, not by luck, but by distance. The magnetar's terrifying energy was a testament to the violence of the cosmos, but for now, it's a storm we observed safely through the window of interstellar space. The danger was real. The proximity wasn't. The flare from SGR 1806-20 was a monumental display of cosmic power, but it also sparked a much deeper, unsettling question among scientists and the public alike. What if this had happened closer to Earth? And perhaps more critically, could it happen again? The idea that a magnetar within our galactic neighborhood could unleash a similar or even stronger burst of energy is not just theoretical, it's a genuine concern rooted in astrophysical possibility. To explore this possibility, we need to start with what we know about magnetars and how common they are. Magnetars are a rare subclass of neutron stars. Only about 30 have been confirmed in the Milky Way so far. But astronomers suspect that this number represents just a tiny fraction of the actual population. Many could be hiding in dense regions of space, obscured by gas and dust, or in quiet phases where they're not flaring or pulsing in any noticeable way. If SGR 1806-20, which is 50,000 light-years away, could affect our ionosphere and saturate satellite detectors, then a similar object just a few thousand light-years away, or worse, a few hundred, could be catastrophic. There are magnetars closer to Earth than SGR 1806-20. For example, 1E2259 plus 586 is about 10,000 light-years away, and XTJ1810-197 is roughly 8,000 light-years distant. These are considered relatively close in galactic terms. The real nightmare scenario, however, involves a magnetar flare occurring within 1,000 light-years. At that range, the effects on Earth could be far more serious. Let's imagine such a scenario for a moment. A magnetar, say 500 light-years away, undergoes a giant flare like the one SGR 1806-20 released. That's only 1% of the distance that protected us in 2004. The gamma-ray and X-ray energy wouldn't have as much space to disperse, and the intensity hitting Earth's atmosphere would be dramatically higher. This could cause severe damage to the ozone layer, allowing harmful ultraviolet radiation from the sun to reach the surface, possibly triggering biological mutations, ecological collapse, or even mass extinctions. This isn't just science fiction. In fact, some scientists have hypothesized that past mass extinction events may have been triggered by nearby cosmic explosions, including supernovae or possibly magnetar flares. One potential candidate is the Ordovician, Silurian extinction around 450 million years ago. Evidence suggests that a gamma-ray burst or similar high-energy event could have stripped away part of Earth's ozone layer, dramatically impacting marine life. But how likely is such an event to happen within human timescales? Thankfully, not very. The odds of a giant flare from a magnetar within 1,000 light-years occurring in the next few centuries are extremely low. These stars are rare, and even among them, such catastrophic outbursts are rarer still. Most magnetars flare regularly but at much lower intensities. Giant flares like the one from SGR 1806-20 are thought to occur once every few thousand years, per magnetar. Considering how few magnetars are located within this danger zone, the probability of one flaring in our cosmic neighborhood during our lifetimes is statistically tiny. But the problem is uncertainty. Because magnetars are hard to detect and often shrouded in gas and dust, it's possible that a dark, or inactive magnetar could exist relatively close to Earth, and we might not know until it flares. One might be lurking in the galactic halo, or even behind the Sun from our perspective. With every improvement in X-ray and gamma-ray astronomy, we discover more transient, faint objects that could turn out to be dormant magnetars. Some of the mysterious fast radio bursts, FRBs, observed in the cosmos may even come from distant magnetars. We'll touch on that in a later segment. To mitigate these risks, astronomers are actively scanning the sky with sensitive space observatories like NASA's NICER, NuSTAR, Fermi Gamma-Ray Space Telescope, and ESA's Integral. These instruments are capable of detecting subtle changes in X-ray and gamma-ray output from known and unknown sources. If a nearby magnetar began ramping up its activity, we might be able to get a heads-up, days or weeks in advance, if we're lucky. But unlike a comet or asteroid, we can't deflect or shield ourselves from a blast of high-energy photons. The best we can do is observe, predict, and prepare. Interestingly, some scientists have even proposed including magnetar monitoring as part of global defense initiatives, alongside programs like planetary defense against asteroids. The logic is that while the risk is low, the consequence of such an event could be civilization-altering. And because we now rely so heavily on satellite communications, GPS, and long-range electrical infrastructure, the ripple effects of a strong nearby magnetar flare could disable large chunks of modern society, if not the biosphere itself. In summary, while the flare from SGR 1806-20 was spectacularly distant, similar objects do exist much closer. The chance of such an event happening near Earth during our lifetimes is very low, but not zero. It's a cosmic roulette game played across millions of years. And though the chamber is mostly empty, there's always the possibility of a live round. In the vast realm of stellar evolution, few end states are as extreme and mind-bending as neutron stars, pulsars, and magnetars. They are all born from the same cataclysmic event, a supernova explosion following the death of a massive star. But they diverge into different forms depending on specific conditions such as mass, spin rate, and magnetic field strength. To understand how a magnetar like SGR 1806-20 can be so unique and powerful, we need to explore how it compares to its cosmic cousins, pulsars and neutron stars in general. Let's begin with the common ancestor, the neutron star. When a massive star, typically between 10 to 25 times the mass of our Sun, exhausts its nuclear fuel, it collapses under its own gravity. The outer layers explode outward in a brilliant supernova, but the core implodes. The collapse is so extreme that protons and electrons are crushed together to form neutrons, resulting in a dense sphere of neutron-rich matter. What's left behind is a neutron star, an object with a mass greater than the Sun's, squeezed into a city-sized sphere only about 20 kilometers in diameter. A single teaspoon of neutron star material would weigh around 1 billion tons. All pulsars and magnetars are neutron stars, but not all neutron stars become pulsars or magnetars. Think of neutron stars as a broad class, with pulsars and magnetars as specialized subclasses. The differences lie in their magnetic fields, spin rates, and emissions. Pulsars are neutron stars that emit beams of electromagnetic radiation, usually in the radio, X-ray, or gamma-ray spectrum, from their magnetic poles. Because their magnetic axis is not aligned with their rotational axis, these beams sweep across the sky like lighthouse beacons. When one of those beams happens to point toward Earth, we detect a highly regular pulse of energy, hence the name pulsar. Some pulsars spin incredibly fast, up to hundreds of times per second, and their timing is so precise they're sometimes used as cosmic clocks. The magnetic field of a typical pulsar is extremely strong by Earth standards, about 10 superscript 1 superscript 2 Gauss, but it pales in comparison to a magnetar. The energy of a pulsar comes primarily from its rotational speed. Over time, pulsars slow down as they lose energy through radiation and particle winds. They tend to live long, gradually dimming and spinning more slowly over millions of years. Now enter the magnetar, the most exotic and violent of the neutron star family. While they are also neutron stars, magnetars have magnetic fields that are 1,000 times stronger than those of pulsars, in the range of 10 superscript 1 to 10 superscript 1 Gauss. To put that in perspective, Earth's magnetic field is about 0.5 Gauss. A refrigerator magnet is about 50 Gauss. A hospital MRI machine? Roughly 10,000 Gauss. A magnetar's magnetic field is so intense that if one were located within 1,000 kilometers of Earth, it could wipe the data off credit cards, disrupt all electronics, and possibly even distort the shapes of atoms in human tissue. Fortunately, no known magnetars are that close. Unlike pulsars, which lose energy gradually and predictably, magnetars can experience violent outbursts known as giant flares or magnetic star quakes. These are often triggered by the instability of their own magnetic fields, which can twist, snap, or reconfigure due to immense internal pressures. These flares release vast quantities of X-rays and gamma rays in mere fractions of a second, making them some of the brightest events in the universe, just like the 2004 eruption of SG1806-20. The spin rates of magnetars also differ. Most pulsars are born spinning rapidly, sometimes hundreds of times per second, but magnetars usually have slower rotation periods, typically in the range of 2 to 12 seconds. That might seem slow, but it's still remarkably fast considering their density. The reason magnetars spin more slowly is that their intense magnetic fields create enormous torque, which breaks their rotation much faster than in ordinary pulsars. In fact, a young neutron star with a very strong magnetic field will often spin down quickly and become a magnetar. Over thousands of years, as the magnetic field decays, the magnetar might then become indistinguishable from a quiet neutron star, one without bursts, pulses, or flares. One of the most interesting aspects of magnetars is that they don't always exhibit predictable behavior. Pulsars tend to follow a consistent beat, like a metronome, but magnetars can go quiet for years and then suddenly erupt with no warning. Some even exhibit both magnetar and pulsar behavior, suggesting there's a continuum of characteristics between these objects, rather than clean categories. Another key difference lies in their environments. Pulsars are often found in the remnants of supernovae, such as the Crab Nebula, and many are located in relatively quiet regions of the galaxy. Magnetars, however, are often found in regions of intense star formation, where massive stars are born and die in close succession. This environment likely contributes to their formation. It's thought that only the most massive progenitor stars, those that explode quickly after a short life, produce the extreme conditions needed to generate a magnetar. Moreover, magnetars are short-lived by comparison. Their magnetic fields decay relatively quickly, within 10,000 to 100,000 years. After that, they may transition into more conventional neutron stars or become almost undetectable. This decay also makes them rare. There could be millions of neutron stars in the galaxy, but only a few dozen active magnetars at any given time. SGR1806-20 is considered one of the most extreme magnetars because of the sheer magnitude of its flare, the strength of its magnetic field, and its relative youth. It represents a pinnacle of stellar violence, a type of neutron star that not only bends the rules of physics but threatens to tear them apart. As our instruments become more sensitive, we're beginning to suspect that some mysterious X-ray and radio phenomena in the sky may be coming from transitional objects, neutron stars that don't fit neatly into the pulsar or magnetar category. It's possible that some pulsars will evolve into magnetars, or that aging magnetars become ordinary neutron stars. The more we study these exotic remnants, the more we realize that the lines between them are not hard borders, but blurred transitions. SGR1806-20 stands out as a shining, terrifying reminder that the universe still holds stellar entities capable of reshaping not just scientific understanding, but perhaps the destiny of any planet too close when they lose control. Magnetars like SGR1806-20 are infamous for their sudden, violent outbursts, moments when they unleash more energy in a fraction of a second than the sun emits over tens of thousands of years. But what exactly triggers these colossal bursts? One of the most compelling explanations lies in the phenomenon known as a magnetic quake, sometimes called a star quake. To grasp what a magnetic quake entails, it helps to first imagine the internal structure of a magnetar. While neutron stars in general are made of incredibly dense matter, primarily neutrons squeezed together so tightly that a sugar cube-sized amount would weigh billions of tons, a magnetar takes this density to an extreme. What sets magnetars apart is their enormous magnetic field, often reaching or exceeding 10 superscript 1 Gauss. This magnetic field isn't just a passive feature, it actively stresses and strains the star's solid crust, which is thought to be a thin, rigid outer shell made of neutron-rich nuclei. Over time, this magnetic field is not static. It twists, contorts, and shifts due to complex interactions between the star's interior and its magnetosphere, the region dominated by its magnetic field. This creates immense tension inside the crust. Eventually, this tension builds to a breaking point, much like the buildup of tectonic stress causes earthquakes on Earth. When the crust can no longer withstand the stress, it suddenly cracks or snaps, in a process analogous to an earthquake. This is the magnetic quake, a rapid realignment of the crust and magnetic field lines releasing an enormous amount of energy almost instantaneously. The cracking can be so violent that it shakes the entire star, sending shock waves through its interior and magnetosphere. What happens next is where the spectacle truly begins. The sudden fracture of the crust releases a burst of electromagnetic energy, primarily in the form of gamma rays and X-rays. The energy cascades outward, accelerated by the intense magnetic fields, producing the giant flare that we detect from Earth. The event is so powerful that the flare from SGR1806-20 in 2004 temporarily ionized Earth's upper atmosphere, despite occurring 50,000 light-years away. The magnetic quake theory aligns well with observations of magnetar flares because it explains the suddenness and enormity of these events. It also accounts for why these flares are often preceded by smaller bursts or precursors, which could be the early fractures or magnetic rearrangements leading up to the main quake. Furthermore, magnetic quakes are thought to be accompanied by the ejection of plasma and particles from the magnetar's magnetosphere. This creates a complex and dynamic environment that can be studied using various wavelengths, from radio waves to gamma rays, allowing astronomers to piece together the timeline and mechanics of the flare. The magnetic quake doesn't just impact the star's outer shell, it can ripple deep into the star's core, influencing the exotic, ultra-dense matter inside. This interaction might affect the star's rotation or cause slight variations in its timing signals, which can be detected by sensitive telescopes on Earth. These subtle changes provide clues that help scientists understand not only the quake itself but the extreme physics governing magnetar interiors. Some models also suggest that magnetic quakes could trigger oscillations or star quakes, modes, somewhat like ringing a cosmic bell. These vibrations could persist for minutes after the initial flare and may be detectable as quasi-periodic oscillations, QPOs, in the emitted X-ray light. Observations of QPOs after magnetar flares support this idea and offer a unique window into the star's internal structure and composition. Importantly, the magnetic quake theory provides insight into why not all magnetar flares are equal. Smaller quakes might produce minor bursts, or no detectable flare at all, while the largest fractures can unleash the kind of energy that shook Earth's ionosphere in 2004. This variability helps explain the sporadic and unpredictable nature of magnetar activity. SGR1806-20's 2004 flare remains the most powerful observed magnetar flare and is often cited as the textbook example of a magnetic quake gone wild. The star quake released energy on such a scale that it saturated detectors across the globe, causing a ripple effect in Earth's magnetosphere and ionosphere. Despite the intense burst, the star itself remained intact, its crust momentarily rearranged but resilient, ready for the next cycle of magnetic stress. Understanding magnetic quakes doesn't just deepen our knowledge of magnetars, it also enhances our grasp of neutron star physics, the behavior of ultra-dense matter, and the limits of magnetic field strengths in the universe. It pushes the boundaries of how matter behaves under extreme conditions and opens doors to new physics beyond what can be recreated on Earth. Thus, the violent flare from SGR 1806-20 was more than just a cosmic light show. It was a manifestation of one of the most extreme geological processes known, a magnetic quake shaking a star thousands of light years away, reverberating all the way to our tiny blue planet. The incredible journey of the X-rays emitted by SGR 1806-20's 2004 flare is as fascinating as the flare itself, spanning a vast cosmic distance of approximately 50,000 light-years before finally reaching Earth's detectors. To fully appreciate the significance of this, it's essential to understand the nature of electromagnetic radiation, the scale of the universe, and the challenges that these X-rays faced on their epic voyage. When SGR 1806-20 erupted in that sudden, explosive burst, it emitted a flood of high-energy photons, mostly X-rays and gamma rays, fanning out across the cosmos at the speed of light, which is roughly 299,792 kilometers per second, or about 186,282 miles per second. These photons, despite being massless, carry energy and momentum, racing away from the magnetar in all directions. A light year is the distance light travels in one Earth year, approximately 9.46 trillion kilometers, 5.88 trillion miles. So when we say the flare's X-rays traveled 50,000 light years, it means that the event we detected in 2004 actually occurred 50,000 years ago in the star's reference frame, and those photons have been journeying through space for tens of millennia before finally arriving here. This immense distance puts the scale of our galaxy into perspective. The Milky Way is a barred spiral galaxy, roughly 100,000 light-years across. SGR 1806-20 resides in a dense star-forming region near the galactic center, in a cluster of massive stars buried deep within cosmic dust and gas clouds. Despite these obstacles, the high energy and penetrating power of X-rays and gamma rays allowed them to traverse this environment relatively unscathed. The reason high-energy electromagnetic radiation like X-rays can travel so far lies in their short wavelengths and high frequencies. Unlike visible light, which can be scattered or absorbed by dust and gas in the interstellar medium, gamma rays and X-rays are energetic enough to cut through much of the obscuring material that permeates the galaxy. Still, some absorption and scattering do occur, which is why distant X-ray sources can sometimes be dimmer or harder to detect. Another important factor aiding this journey is the vacuum of space, where there are no air molecules to scatter or absorb the radiation. Once the photons leave the vicinity of the magnetar and pass beyond the immediate stellar neighborhood, they travel largely unhindered. The interstellar medium, ISM, between stars is extremely sparse, with an average of about 1 atom per cubic centimeter. Although this gas can absorb some radiation, the effect on high-energy photons over vast distances is minimal compared to lower-energy light. During their journey, the photons effectively travel in straight lines at constant speed. Since the speed of light is the cosmic speed limit, no information or energy can travel faster, so the moment we detect these photons marks the exact moment the flare's photons arrived at our detectors. On December 27, 2004, when the flare's photons reached Earth, they were detected by satellites and space telescopes designed to observe high-energy phenomena. These instruments include the Rossi X-ray Timing Explorer, RXD, the Swift Gamma-ray Burst Mission, and the International Gamma-ray Astrophysics Laboratory, Integral, among others. Some detectors were momentarily overwhelmed or saturated because the flare was so intense, a testament to its incredible energy. The arrival of the photons triggered a chain reaction in Earth's own atmosphere. Specifically, the ionosphere, the charged upper layer of Earth's atmosphere, responded to the sudden influx of high-energy radiation. This caused disturbances in radio wave propagation and changes in the Earth's magnetic environment, detectable by instruments around the globe. It's remarkable to think that particles emitted in a cosmic cataclysm 100 millennia ago finally collided with sensors built by human hands, allowing us to piece together a story from across the galaxy. The photons' unerring precision, traveling through the void of space for 50,000 years, underlines how interconnected the universe is, how events in the farthest reaches can ripple through space and time, reaching us and informing our understanding of stellar extremes. This journey also highlights the challenges astronomers face in studying such phenomena. Because the flare's light took 50,000 years to arrive, we are observing an event from the distant past, not the present state of the magnetar. In other words, SGR 1806-20 as it exists now may have changed drastically, or even ceased to exist in its previous form. This time delay is intrinsic to all astronomical observations. Looking at the universe is always looking back in time. The long distance also means that any potential flare occurring closer to Earth would be far more dangerous, as the energy wouldn't have the opportunity to dissipate or be absorbed along the way. The Earth's relative safety partly comes from this sheer distance, combined with the directionality and spread of the burst. In summary, the X-rays from SGR 1806-20's flare traveled 50,000 years across nearly the entire breadth of our galaxy, passing through dust, gas, and the vacuum of space at the speed of light. Their arrival on Earth not only marked one of the most powerful cosmic events ever recorded but also allowed scientists to probe the physics of magnetars and the nature of extreme magnetic fields. Speculating what would happen if a magnetar flare like the one from SGR 1806-20 occurred much closer to Earth immediately invokes a scenario that teeters on the edge between cosmic wonder and existential threat. The flare we observed in 2004 was staggeringly powerful despite occurring 50,000 light-years away, but proximity is everything when it comes to the destructive potential of such an event. To understand the implications, let's unpack the multi-layered consequences if such a flare were to erupt within, say, a few hundred or even a few thousand light-years from our planet. First, it's critical to grasp the magnitude of the energy released by SGR 1806-20 during its giant flare. The burst unleashed roughly 10 to the power of 46 ergs of energy in less than a tenth of a second. To put this into perspective, this single event emitted more electromagnetic energy than the Sun does over 100,000 years, compressed into a mere instant. The intensity of gamma rays and X-rays blasting out from the magnetar saturated detectors on satellites designed for such purposes and caused measurable disturbances in Earth's ionosphere, despite the gargantuan distance. Now, imagine that energy released 1,000 times closer. The immediate and most profound effect would be a catastrophic burst of intense gamma radiation striking Earth's upper atmosphere. Gamma rays, being highly energetic and penetrating, would interact with molecules in the ionosphere and stratosphere, causing rapid ionization and chemical reactions. This would lead to the destruction of the ozone layer, the thin protective shield that blocks harmful ultraviolet (UV) radiation from the Sun. The depletion of the ozone layer would expose life on Earth to increased levels of UV radiation, leading to widespread damage to DNA in living organisms, and disruptions to marine ecosystems, especially phytoplankton, which form the foundation of aquatic food webs. Beyond ozone depletion, the intense burst would also induce a cascade of electromagnetic disturbances in Earth's magnetosphere and atmosphere. The sudden influx of charged particles and high-energy photons could generate massive geomagnetic storms, potentially crippling satellite systems, disrupting power grids, and affecting communication and navigation systems worldwide. In modern civilization, such disruptions could lead to cascading failures in infrastructure, financial systems, and emergency services, exacerbating the natural disaster caused by the radiation itself. The ionospheric disturbances detected from the 2004 flare were already strong enough to impact radio communication for a brief time despite the vast distance. At closer range, these effects would be orders of magnitude more severe. The geomagnetic storms could last for hours or even days, posing significant risks to astronauts in space, high-altitude aircraft, and even high-latitude populations more vulnerable to radiation exposure. From a biological perspective, the ecological impact would be profound. The sudden increase in UV radiation due to ozone depletion would damage terrestrial and marine ecosystems. Phytoplankton, which contribute about half of Earth's oxygen production through photosynthesis, are particularly sensitive to UV light. A collapse of phytoplankton populations would disrupt the marine food chain and global oxygen cycles, affecting all life forms dependent on these systems. Moreover, ionizing radiation from the flare could directly cause mutations in living organisms, especially if the event were prolonged or repeated. This has led some scientists to speculate that magnetar flares, if occurring close enough and with sufficient frequency, could contribute to mass extinction events in Earth's geological history, although direct evidence for such a connection remains elusive. There is also a question of atmospheric chemistry changes beyond ozone depletion. The burst would produce nitrogen oxides, NOx, in the upper atmosphere, which can further catalyze ozone destruction. The atmospheric heating caused by the energy deposition might alter weather patterns, potentially leading to climatic instability. One of the more terrifying possibilities is the effect on Earth's own magnetic field. Although Earth's magnetic field is generated deep within its core and is incredibly resilient, a sudden and intense external magnetic disturbance, such as one produced by a nearby magnetar flare, could cause temporary, severe disruptions. This would reduce Earth's magnetic protection against cosmic rays and solar wind, exposing the surface and biosphere to enhanced radiation. It's important to emphasize that such extreme events are thankfully rare, and magnetars are incredibly scarce in our galaxy. The nearest known magnetars are thousands of light-years away, reducing the immediate risk. However, if a magnetar were to be discovered within a few hundred light-years, scientists would undoubtedly monitor it closely for flare activity. Another consideration is the directional nature of magnetar flares. Unlike supernovae, which explode relatively isotropically, in all directions, magnetar flares may be beamed or concentrated along certain magnetic axes. This means that even if a magnetar flare occurs nearby, Earth might avoid the worst of the radiation simply by not lying in the direct path of the beam. But this also means that a nearby magnetar firing a flare in Earth's direction would be catastrophic. What about the long-term survivability of humanity? While the immediate burst of radiation and atmospheric damage would be devastating, it's unlikely to cause outright extinction. Life on Earth has endured and adapted through much harsher conditions over billions of years. However, the consequences for human civilization would be severe, with potential mass casualties, global food chain disruptions, and a long recovery period. Technological infrastructure would be particularly vulnerable. Satellites could be fried by the intense radiation, plunging Earth into a communication blackout. Power grids could fail under geomagnetic storm conditions, causing widespread outages. Repairing and restoring technology-dependent societies could take years, if not decades. One silver lining is that Earth's atmosphere, despite being damaged, provides a significant protective buffer. The flare's X-rays and gamma rays would not penetrate the surface directly, sparing people from immediate radiation sickness unless they were in space or at high altitudes. Still, the indirect effects on food supply, climate, and health could cause global humanitarian crises. Speculative fiction aside, astrophysicists and planetary defense researchers are keenly aware of these risks and continually scan the skies for potential threats. While magnetars pose a unique and serious hazard, they are only one among many cosmic dangers that humanity must consider in its ongoing quest to understand its place in the universe. This scenario underscores the importance of studying objects like SGR 1806-20, not just to marvel at their extreme physics but to prepare for potential cosmic events that could impact our home planet. Monitoring magnetars, understanding their behavior, and developing mitigation strategies, such as hardening satellites and communication systems, are critical for future planetary defense. In conclusion, if a magnetar flare as powerful as SGR 1806-20 erupted close to Earth, it would be an event of profound and far-reaching consequences. From atmospheric devastation and ecological disruption to technological chaos and potential threats to human health, the effects would ripple through every facet of life on Earth. Fortunately, the immense distances between us and known magnetars provide a cosmic buffer, but vigilance and study remain essential. The question of whether a magnetar flare like the one from SGR 1806-20 could trigger a mass extinction on Earth takes us into the fascinating intersection of astrophysics, geology, and biology. Mass extinctions, the sudden, widespread die-offs of a large proportion of Earth's species, have punctuated our planet's history, shaping the evolutionary trajectory of life. The causes of these extinctions are varied and often complex, including massive volcanic eruptions, asteroid impacts, climate shifts, and more. But could an astronomical event, specifically a magnetar flare, be powerful enough to disrupt life on Earth to such a catastrophic degree? To begin, it's important to understand the scale of impact that high-energy radiation from magnetars can have on Earth's atmosphere and biosphere, as briefly touched upon in the previous discussion about closer magnetar flares. The flare from SGR1806-20 was immensely energetic, and even from a distance of 50,000 light-years, it caused measurable disturbances in Earth's ionosphere. If a similar event occurred closer, within a few thousand light-years, it could drastically alter atmospheric chemistry, particularly by depleting the ozone layer. The ozone layer is crucial because it blocks the sun's harmful ultraviolet, UV, radiation from reaching the surface. UV radiation can damage DNA, leading to mutations and increased mortality rates in many organisms, particularly those living in the ocean's upper layers and terrestrial surface dwellers exposed to sunlight. A significant depletion of ozone could thus increase biological stress dramatically. Modeling studies on atmospheric chemistry changes induced by intense gamma-ray bursts, GRBs, which share energetic similarities with magnetar flares, have suggested that such events could lead to prolonged ozone depletion lasting years to decades. This would cause a sustained period of heightened UV radiation, which could trigger ecological collapses in sensitive ecosystems. But could this trigger a mass extinction? Some scientists argue yes, particularly if such a burst were intense enough and close enough. The damage would not only come from radiation but also from secondary effects. For instance, changes in atmospheric chemistry might lead to climate disruptions, including global cooling caused by increased nitrogen oxides blocking sunlight. This nuclear winter-like scenario could reduce photosynthesis, further stressing ecosystems. Moreover, in the oceans, phytoplankton, the base of the marine food chain, are highly vulnerable to increased UV radiation. Phytoplankton play a vital role in oxygen production and carbon cycling. Their decline would cascade through the marine food web, affecting everything from tiny crustaceans to large marine mammals. A collapse of marine ecosystems could impact terrestrial species relying on marine food sources. Several mass extinctions in Earth's history, including the late Ordovician and the Devonian extinctions, coincide with evidence of environmental stress that could have involved increased radiation or atmospheric changes. Some researchers have speculated that a nearby GRB or magnetar flare might have been a contributing factor, though direct evidence remains elusive. An intriguing hypothesis relates to fast radio bursts, FRBs, mysterious, powerful radio signals thought by some to be connected to magnetar activity. If magnetar flares can produce bursts of high-energy radiation accompanied by FRBs, then these cosmic events might be more common and potentially impactful than currently appreciated. However, it's also important to note that Earth has a natural shield. Its magnetic field and atmosphere provide robust protection against cosmic radiation. The magnetic field deflects charged particles, while the atmosphere absorbs much of the harmful radiation. For a magnetar flare to cause a mass extinction, the event would likely have to be relatively close, within a few thousand light-years, and direct a concentrated beam toward Earth. This brings us back to probability. Known magnetars are rare and generally distant from Earth. The chances of a giant flare hitting Earth directly and closely enough to cause mass extinction are extremely low on human timescales. Nevertheless, over geological timescales, such events cannot be ruled out entirely. Furthermore, geological records can be difficult to interpret. The signature of a magnetar-induced extinction might be subtle or overlapping with other causes, making it challenging to attribute definitively. In summary, while the idea that magnetar flares like SGR1806-20 could trigger mass extinctions on Earth remains speculative, it is scientifically plausible given their capacity to disrupt atmospheric chemistry, degrade the ozone layer, and increase harmful radiation. These changes could cascade through ecosystems, causing widespread biological stress and potential die-offs. Whether this has happened in Earth's past or could happen in the future remains an open question, a powerful reminder of how cosmic events might shape life on our planet. The flare from SGR 1806-20 in December 2004 was not only a phenomenal cosmic event but also a rare instance where Earth's own atmosphere responded measurably to an extraterrestrial burst of energy. Despite the magnetar being about 50,000 light-years away, the intense flood of gamma rays and X-rays from its flare temporarily altered the state of Earth's ionosphere, providing a fascinating real-world demonstration of how distant cosmic phenomena can directly influence our planet's upper atmosphere. To understand this interaction, it's important first to grasp what the ionosphere is. The ionosphere is a layer of Earth's atmosphere extending roughly from about 60 kilometers, 37 miles, to 1,000 kilometers, 620 miles, above the surface. It is characterized by a high concentration of ions and free electrons created primarily by solar radiation, mainly ultraviolet, UV light and X-rays, that ionizes atmospheric gases. This layer plays a critical role in radio communication and navigation, as it can reflect and refract radio waves, enabling long-distance transmission. When the giant flare from SGR 1806-20 erupted, it sent a brief but incredibly intense pulse of gamma rays and X-rays across the galaxy, including toward Earth. These high-energy photons reached our planet's ionosphere in roughly 50,000 years, traveling at the speed of light, arriving in just a fraction of a second. Unlike sunlight, which delivers steady and relatively moderate radiation, the magnetar flare was a sudden, intense spike in high-energy radiation. Upon arrival, these gamma rays and X-rays interacted with molecules in the ionosphere, stripping electrons from atoms and molecules at an accelerated rate, dramatically increasing ionization levels. This rapid and intense ionization caused a sudden enhancement in the electron density in the lower ionosphere, particularly in the D layer, which normally experiences lower ionization during the night. One direct consequence was a disturbance in very low frequency, VLF, radio wave propagation. These VLF waves rely heavily on the state of the ionosphere to reflect and travel long distances. Observatories and monitoring stations around the world detected sudden changes in VLF radio signals, indicating that the ionosphere's reflective properties had been altered. This was one of the first clear pieces of evidence that an astrophysical event so distant could measurably impact Earth's atmospheric layers. Additionally, the flare caused an increase in ionospheric conductivity, affecting the Earth's global electric circuit. This increased conductivity temporarily changed the electrical environment of the atmosphere, potentially influencing cloud formation and weather patterns, though such secondary effects are harder to confirm. The ionospheric disturbance lasted several minutes before gradually subsiding as the additional ionization recombined and normal solar-driven ionospheric conditions reasserted themselves. While the effect was brief, it was powerful enough to demonstrate that Earth is not isolated from cosmic radiation bursts, even those originating from tens of thousands of light-years away. Interestingly, this event was comparable in some ways to solar flares, eruptions on the Sun that also flood Earth's ionosphere with radiation and charged particles. However, the SGR 1806-20 flare's energy was concentrated over a much shorter timescale and in higher energy gamma rays, making the ionospheric impact more sudden and intense, though less prolonged than typical solar storms. These observations have practical implications. For instance, sudden ionospheric disturbances can affect GPS accuracy, radio communications, and even radar systems. The 2004 flare provided an unexpected real-world test case that expanded our understanding of how high-energy astrophysical phenomena can influence Earth's space weather environment. From a scientific perspective, the ionospheric response to SGR 1806-20's flare gave astronomers and atmospheric physicists valuable data on how gamma rays interact with planetary atmospheres. This information can be extrapolated to study other planets with ionospheres, such as Mars or Venus, and even to assess the habitability of exoplanets orbiting magnetars or other high-energy astrophysical sources. In summary, although the flare from SGR 1806-20 was a cosmic event occurring light-years away, its impact on Earth's ionosphere was unmistakable. The intense burst of gamma rays temporarily increased ionization levels in the ionosphere, disrupted radio wave propagation, and altered the electrical properties of the upper atmosphere. This rare interaction provided a tangible reminder of how the vast universe can influence our home planet in profound and sometimes surprising ways. The idea that a magnetar, such as SGR1806-20, one of the most powerful magnetars ever observed, could destroy or significantly disrupt Earth's magnetic field is a provocative and captivating subject. It taps into deep questions about the fragility and resilience of our planet's magnetic shield and how external cosmic forces could influence it. To explore this idea fully, we need to examine the nature of Earth's magnetic field, the characteristics of magnetar flares, and the ways in which extreme cosmic radiation might interact with planetary magnetospheres. Earth's magnetic field, also known as the geomagnetic field, is generated deep within the planet by the dynamo effect, a complex process arising from the movement of molten iron in Earth's outer core. This field extends far into space, creating the magnetosphere, a protective bubble that deflects charged particles from the solar wind and cosmic rays, shielding the atmosphere and surface from harmful radiation. Without this magnetic shield, life on Earth would be exposed to intense cosmic and solar radiation, making the surface far less hospitable. Magnetars, on the other hand, possess magnetic fields billions of times stronger than anything produced naturally on Earth. For perspective, Earth's magnetic field strength averages about 25 to 65 microteslas, whereas a magnetar's field can reach strengths of 10 to the power of 10 to 10 to the power of 11 teslas. This is an almost incomprehensible difference, reflecting the extreme physics governing neutron stars, the ultra-dense remnants of massive stars that have exploded as supernovae. When a magnetar like SGR1806-20 unleashes a giant flare, it releases a sudden burst of gamma rays, X-rays, and energetic particles, accompanied by a dramatic rearrangement or quake in its magnetic field structure. This flare, although occurring tens of thousands of light-years away, packed more energy into a fraction of a second than the Sun emits in 100,000 years. Such intensity prompts the natural question, could such an outburst, if closer, overwhelm Earth's magnetic defenses? The short answer is that under certain conditions, yes, a sufficiently powerful magnetar flare occurring near enough to Earth could severely disrupt our magnetic field and magnetosphere, although outright destruction of the magnetic field is highly unlikely. To break this down, consider what happens when Earth's magnetosphere is bombarded by energetic particles and radiation. Solar storms, such as coronal mass ejections, CMEs, frequently send streams of charged particles toward Earth. These storms can compress the magnetosphere, induce geomagnetic storms, and cause temporary disturbances such as auroras and disruptions in communications and power grids. However, Earth's magnetic field has shown resilience, bouncing back from these events relatively quickly. A magnetar flare, however, would be orders of magnitude more intense. If one were close enough, within a few thousand light-years, and oriented such that Earth lay in the direct path of its beam, the influx of high-energy gamma rays and particles could deliver a massive dose of ionizing radiation into the upper atmosphere and magnetosphere. This sudden onslaught could induce rapid changes in the electric currents flowing within the magnetosphere, destabilizing the magnetic field lines. In particular, the energetic photons from a magnetar flare could ionize the upper atmosphere and exosphere to unprecedented levels, increasing conductivity and altering the current systems that sustain the magnetosphere. The sudden input of energy might cause magnetic reconnection events, where magnetic field lines break and reconnect violently, triggering geomagnetic storms far beyond those caused by solar activity. Such an intense geomagnetic storm could temporarily distort the shape and strength of Earth's magnetic field, possibly compressing it closer to the planet's surface. This would reduce the size of the magnetosphere and expose satellites, spacecraft, and potentially even the surface to increased radiation. However, the Earth's magnetic field is generated by processes deep within the planet's core, which operate on geological timescales and are not easily altered by external electromagnetic forces. Thus, the core dynamo itself would not be destroyed by an external magnetar flare. Instead, the disruption would be temporary, affecting the magnetosphere and upper atmospheric layers. That said, if such intense bursts occurred repeatedly over time or with sustained intensity, they could induce longer-lasting perturbations. For example, repeated strong geomagnetic storms can cause changes in the ionosphere and atmosphere that may indirectly affect the planet's climate or biological systems. Another consideration is the potential impact on Earth's radiation belts, the Van Allen belts, zones of trapped energetic particles. A strong magnetar flare could inject massive amounts of high-energy particles into these belts, greatly increasing their intensity and radiation hazards for orbiting satellites and astronauts. The possibility of a magnetar flare causing a collapse or reversal of Earth's magnetic field is more speculative, and not strongly supported by current geophysical understanding. Magnetic field reversals, which have occurred many times in Earth's history, are believed to originate from changes in the core dynamo rather than from external cosmic events. Still, large external influences might play some role in triggering or accelerating these processes, although this remains a subject of active research and debate. Importantly, Earth has not yet experienced a magnetar flare close enough or powerful enough to cause major magnetic disruptions. The 2004 SGR1806-20 flare reached Earth with enough intensity to disturb the ionosphere but did not measurably affect the geomagnetic field beyond minor, temporary perturbations. This suggests that while the idea of a magnetar destroying Earth's magnetic field is intriguing, it is not a realistic near-term threat. Looking beyond Earth, however, magnetar flares might have devastating effects on the magnetic fields of planets orbiting magnetars or located in close proximity. For any planet with a weaker magnetic field or atmosphere, a giant flare could strip away atmospheric particles, cause extreme radiation exposure, and possibly sterilize the surface. Such considerations are key in understanding the habitability of exoplanets around exotic stars. The extreme magnetic environment of magnetars also challenges our understanding of physics. These stars are laboratories for studying quantum electrodynamics in the strongest magnetic fields known, where phenomena like vacuum birefringence and exotic particle behavior occur. The interaction between magnetar flares and planetary magnetic fields could therefore provide insights into magnetospheric physics under extreme conditions. In conclusion, while a magnetar flare like SGR1806-20 could, if sufficiently close and intense, severely disrupt Earth's magnetic field temporarily, the deep geomagnetic dynamo generating Earth's magnetic field is resilient to such external shocks. The magnetosphere would likely undergo dramatic but transient disturbances, with potential consequences for satellite systems and radiation exposure on Earth. The prospect of permanent destruction or collapse of Earth's magnetic field by a magnetar flare remains highly unlikely given current scientific understanding. Nevertheless, the possibility of such a flare causing severe, even catastrophic effects on planetary environments elsewhere in the universe underscores the profound impact these cosmic powerhouses can have. Their extreme magnetic fields and intense flares are among the most violent phenomena in the cosmos, pushing the boundaries of astrophysics and planetary science. The vastness of the universe and the nature of magnetars like SGR1806-20 naturally lead to the question: how many magnetars are out there, lurking unseen, waiting to unleash their formidable power? The possibility that countless undiscovered magnetars exist throughout our galaxy, and beyond, is a compelling idea that touches on the limits of our observational capabilities, the lifetimes of magnetars, and the ongoing mysteries of stellar evolution. Magnetars are a rare and exotic class of neutron stars distinguished by their extraordinarily strong magnetic fields. They form from the remnants of massive stars that have undergone supernova explosions, leaving behind an ultra-dense core composed mostly of neutrons. Among these remnants, only a small fraction become magnetars, while others become more typical neutron stars or pulsars. To date, astronomers have confirmed only around 30 magnetars, although this number is steadily increasing with improved observational tools and methods. But this count likely represents only a tiny fraction of the total magnetar population. One major reason magnetars remain so elusive is their transient and often unpredictable nature. Many magnetars are discovered not through steady emissions, but rather via sudden bursts of X-rays or gamma rays, like the giant flare from SGR 1806-20, that reveal their presence. These bursts can be rare, separated by years or decades, making it difficult to catch a magnetar in the act. In their quieter phases, magnetars can be relatively dim and harder to detect with traditional radio or X-ray telescopes. Another factor complicating their discovery is their typical location. Magnetars often reside in dense, dusty regions of the galaxy, such as stellar nurseries or remnants of supernovae, where interstellar dust and gas absorb or scatter much of their radiation before it reaches Earth. This obscuration can make detection challenging, especially for those magnetars farther away or behind dense clouds of material. Moreover, the lifespan of magnetars as highly active objects is thought to be relatively short on cosmic timescales, perhaps only 10,000 to 100,000 years, before their intense magnetic fields decay and their energetic outbursts diminish. This transient phase means that magnetars represent a fleeting stage in the life of a neutron star. Outside this phase, magnetars might still exist but behave more like typical neutron stars, losing the distinctive flaring activity that draws attention. Given these factors, astronomers believe there is a large population of hidden or dormant magnetars in the Milky Way, simply waiting for a flare or some other event to signal their presence. Some may be so far away or so quiet that their emissions never reach Earth's telescopes, or their signals are buried within background cosmic noise. Recent advances in telescope technology and space-based observatories have started to peel back this veil. Instruments like NASA's Fermi Gamma Ray Space Telescope, the European Space Agency's XMM Newton X-ray Observatory, and other space-based detectors have enhanced sensitivity and coverage, enabling the detection of fainter and more distant magnetar candidates. These tools have expanded the catalog of known magnetars and provided insights into their diverse behaviors and magnetic field strengths. Scientists also speculate that many magnetars might be found in other galaxies, although detecting them at extragalactic distances is extremely challenging. However, some fast radio bursts, FRBs, brief but intense flashes of radio waves originating from far outside our galaxy, have recently been linked to magnetar activity. This connection opens new pathways for discovering magnetars beyond the Milky Way, especially as radio astronomy capabilities improve. There is also an ongoing effort to search for magnetars through indirect means, such as studying supernova remnants with unusual X-ray signatures or searching for peculiar pulsations that hint at ultra-strong magnetic fields. As observational methods and data processing techniques improve, the likelihood of uncovering many more magnetars increases. Furthermore, some theoretical models predict that certain types of massive star collapses could preferentially produce magnetars, suggesting their numbers might be higher than previously assumed. For example, the link between magnetars and some types of gamma-ray bursts hints that these exotic stars could be more common in regions of active star formation or in young galaxies. The discovery of magnetars like SGR 1806-20 that can produce giant flares so powerful they affect Earth from 50,000 light-years away underscores the importance of understanding their population and distribution. Each new magnetar discovered provides crucial data for testing theories about the extreme physics governing magnetic fields, dense matter, and stellar evolution. In conclusion, while only a few dozen magnetars are currently known, the true number of these extreme cosmic objects in the galaxy is almost certainly much higher. Their transient behavior, location in obscured regions, and relatively short active lifetimes contribute to their elusive nature. However, advances in astronomical instrumentation and observational strategies continue to reveal more magnetars, enriching our understanding of these fascinating remnants of stellar death. The prospect of many undiscovered magnetars has implications not only for astrophysics but also for planetary safety and cosmic hazard assessment. If a magnetar were to flare within a few thousand light-years of Earth, the consequences could be severe, emphasizing the need for continued monitoring of these enigmatic stars. Imagine a distant alien civilization residing in a star system not far from a magnetar like SGR 1806-20. The sudden, cataclysmic flare unleashed by such a star would be far more than a spectacular cosmic light show. It could represent an existential threat of unfathomable scale. Speculating on how magnetar flares could affect extraterrestrial life invites us to explore not just the raw physics of these violent bursts, but also the potential fragility of life and technology under such extreme conditions, and the broader implications for habitability across the galaxy. Magnetar flares emit enormous amounts of high-energy radiation, including gamma rays and X-rays, which travel vast distances through space almost unimpeded. For alien civilizations situated within a few thousand light-years of a magnetar flare, the consequences could be dire. Much like the hypothetical effects on Earth, intense radiation would bombard the planet's atmosphere, potentially stripping away protective layers like the ozone and ionosphere, leading to a surge in harmful ultraviolet and cosmic radiation reaching the surface. Such exposure could cause widespread biological damage. Complex molecules essential for life, like DNA and proteins, are vulnerable to high-energy radiation that can break chemical bonds and induce mutations. While some life forms might have evolved protective mechanisms, or life might exist underground or underwater where radiation effects are mitigated, the suddenness and intensity of a giant magnetar flare could overwhelm such defenses. This could lead to mass extinctions, ecological collapse, or at least a severe disruption to biospheres. For technologically advanced civilizations, magnetar flares pose additional challenges. Our own technology is highly sensitive to electromagnetic disturbances. Satellites, power grids, communication systems, and even electronic devices can be disrupted or destroyed by intense electromagnetic pulses and radiation storms. Alien societies relying on similar or even more advanced electronic infrastructure would face similar or greater vulnerabilities. Given the immense energy release of a flare like SG1806-20, the electromagnetic effects could induce large-scale geomagnetic storms on affected planets, potentially frying satellites or causing global communication blackouts. This could cripple navigation systems, defense networks, and scientific instruments, leaving civilizations temporarily or permanently blind to their surroundings. The loss of technological capabilities could have cascading effects on social stability, economies, and even survival in extreme cases. Moreover, magnetar flares may be sporadic and unpredictable. This unpredictability complicates any defensive measures an alien civilization might attempt, making it difficult to shield critical infrastructure or seek shelter ahead of time. Unlike solar storms, which follow somewhat regular cycles and can be forecasted with some accuracy, magnetar flares are rarer, more intense, and less predictable. This increases their potential for catching civilizations off guard. From a broader cosmic perspective, the presence of magnetars and their flares could shape the distribution and evolution of life in galaxies. Regions dense with massive stars, which are the progenitors of magnetars, may be hostile zones where life struggles to develop or survive due to frequent radiation events. Conversely, more quiescent regions farther from such hazards might provide safer cradles for life to flourish. This idea aligns with the concept of the galactic habitable zone, a region in a galaxy thought to be most conducive to life due to a balance of necessary elements, radiation levels, and stellar density. Magnetar flares could be a critical factor influencing this balance, pruning the number of viable habitats in star-forming, magnetar-rich regions. Interestingly, some scientists have proposed that fast radio bursts, FRBs, brief, intense pulses of radio waves observed across the universe, might originate from magnetars. If so, an alien civilization monitoring radio signals might detect such bursts as mysterious or even ominous cosmic phenomena, influencing their understanding of the cosmos and their place within it. For any alien civilization capable of advanced astronomy and astrophysics, detecting a nearby magnetar and understanding its behavior could be crucial. They might develop early warning systems to detect the precursors of flares or even devise methods to shield themselves from radiation bursts. The feasibility of such defenses remains speculative, but it highlights the possible cosmic challenges intelligent life might face. Speculating further, civilizations might attempt to avoid star systems with known magnetars or migrate away from regions with high magnetar density. This cosmic hazard could even influence the patterns of interstellar colonization or exploration, steering civilizations towards safer regions. On a more philosophical level, The knowledge that powerful and violent cosmic events like magnetar flares occur might shape an alien species' culture and worldview. They might revere or fear these stars as harbingers of destruction or cosmic renewal, integrating them into their narratives about creation and survival. In summary, the impact of magnetar flares like SGR1806-20 on alien civilizations could be profound, ranging from biological devastation to technological collapse. The extreme energies and radiation released pose serious hazards to life and infrastructure, especially for civilizations located within a few thousand light-years. These flares likely shape the cosmic landscape of habitability, influencing where and how life can thrive. Understanding these effects extends our view of the universe, emphasizing the dynamic and sometimes hostile environment in which life might exist beyond Earth. Contemplating the survival chances of humanity if a magnetar flare, one as powerful as that from SGR1806-20, were to strike Earth directly is a sobering exercise in cosmic vulnerability. The sheer magnitude of energy released in a fraction of a second by such an event is almost incomprehensible, and although Earth narrowly escaped major harm in 2004 from the distant SGR1806-20 flare, a closer encounter could be catastrophic. To understand the potential survival scenario, it is essential to break down the various effects a direct magnetar flare would have on Earth, and how these would interact with both our natural environment and technological civilization. First and foremost, the primary threat from a magnetar flare comes in the form of intense gamma-ray and X-ray radiation. These high-energy photons can penetrate the upper layers of Earth's atmosphere, specifically the stratosphere and mesosphere, initiating complex chemical reactions. One of the most critical consequences would be the destruction of the ozone layer, which acts as a shield protecting living organisms from harmful ultraviolet (UV) radiation from the sun. Without this protective ozone, the increase in UV radiation reaching the surface would be dramatic. UV radiation can cause widespread DNA damage, mutations, and severe impacts on ecosystems, particularly phytoplankton in the oceans, the foundational component of marine food chains. A collapse in these populations would ripple up the food chain, affecting fish, marine mammals, and ultimately humans. Secondly, the ionization of the upper atmosphere from the magnetar's burst would trigger a powerful geomagnetic storm, disrupting Earth's magnetic field and inducing strong electric currents in the planet's crust. This electromagnetic disturbance could knock out electrical grids, satellite communications, GPS systems, and radio networks, plunging modern civilization into darkness and cutting off vital infrastructure. The technological devastation alone would be staggering. Satellites vital for weather forecasting, navigation, and communication could be permanently damaged. Power grids could face prolonged outages as transformers burn out, or electrical surges overload systems. This would severely hamper emergency response, food supply chains, and medical systems, compounding the immediate biological risks. From a direct health perspective, while the Earth's atmosphere provides significant shielding, a sufficiently close magnetar flare, within a few thousand light-years, could overwhelm this protection, causing increased radiation exposure for life on the surface. However, the atmosphere itself would absorb most of the initial gamma and X-rays, sparing direct exposure to the surface from the most lethal effects. The indirect consequences through atmospheric chemistry changes and electromagnetic disruption are the more pressing threats. Could humans survive such an event? The answer depends on several factors: distance from the magnetar, flare intensity, preparedness, and the resilience of human infrastructure and ecosystems. At distances greater than about 10,000 light-years, the flare's impact might be limited to temporary disruptions and minor ozone depletion. At closer ranges, say within a few thousand light-years, the effects could be severe enough to cause mass extinctions or a collapse of complex ecosystems. Nevertheless, humanity's survival chances improve if some precautions are in place. Underground or underwater shelters could shield populations from harmful radiation and environmental collapse. Advances in technology might enable rapid rebuilding of infrastructure or development of protective technologies, such as artificial ozone generation or electromagnetic shielding. Moreover, a global coordinated response and early warning systems to detect magnetar flares would be critical. Current gamma-ray observatories continuously monitor space for such bursts, potentially providing warnings minutes to hours before a flare's electromagnetic wavefront arrives on Earth, allowing for some mitigation measures. Even with the best preparation, the long-term environmental damage could pose a severe challenge. Global cooling from atmospheric changes, disrupted food production, and societal collapse are real risks. Recovery could take decades or centuries, depending on the scale of the event. In summary, a direct hit from a magnetar flare like SGR1806-20 would pose existential threats to humanity, primarily through atmospheric destruction, radiation-induced biological damage, and technological collapse. Survival is not impossible but would require a combination of fortunate distance, advanced preparation, and resilient social systems. The event would be one of the greatest natural disasters imaginable, reshaping life on Earth and human civilization in profound ways. The eruption of SGR1806-20, one of the most powerful magnetar flares ever observed, has intrigued astrophysicists and sparked a multitude of scientific theories seeking to explain the cause behind such an extraordinary event. Understanding why this magnetar suddenly released an immense burst of energy not only sheds light on the nature of magnetars themselves but also deepens our grasp of the behavior of matter and magnetic fields under the most extreme conditions known in the universe. Several leading theories have emerged, each addressing different mechanisms that could trigger the violent release of energy observed in the flare. One of the foremost theories centers on the concept of magnetic instability within the magnetar's crust and interior. Magnetars possess magnetic fields so strong that they exert enormous stresses on the solid crust, which is thought to be a rigid lattice of neutrons and protons. Over time, as the magnetic field evolves and twists, these stresses accumulate, much like tectonic stresses on Earth's plates. When the stresses exceed the structural integrity of the crust, a sudden fracture or star quake occurs. This star quake disrupts the magnetic field lines, causing them to snap and rearrange violently. The sudden realignment of these ultra-strong magnetic fields releases an immense amount of magnetic energy in the form of high-energy radiation. This magnetic reconnection process is believed to be a primary driver behind magnetar flares like the one from SGR1806-20. The analogy here is somewhat akin to solar flares on the Sun, where magnetic field lines in the solar atmosphere twist and snap, but magnify to an almost incomprehensible scale given the strength of magnetar fields. Another prominent theory proposes that the eruption might be linked to the dynamics of exotic states of matter inside the magnetar's core. Neutron stars, including magnetars, are thought to contain matter at densities exceeding those found in atomic nuclei, potentially forming strange phases of matter like superfluid neutrons or even quark-gluon plasma. Some models suggest that the internal composition of the star could undergo a phase transition, where matter suddenly changes state, releasing energy abruptly. This internal upheaval could disturb the star's magnetic field structure and precipitate a large flare. Such phase transitions could be triggered by the slow cooling and contraction of the star over time, or by accretion of matter from the surroundings. The exact physics of such exotic matter states remains an active area of research, and understanding whether such transitions occur is vital for explaining not only magnetar flares but also the broader physics of ultra-dense matter. A related hypothesis involves the buildup of toroidal magnetic fields inside the magnetar. Unlike the poloidal fields that extend outward like a bar magnet, toroidal fields wrap around the star in donut-shaped loops beneath the surface. If these internal fields become too strong or unstable, they can distort the crust and trigger magnetic field reconfigurations that release energy explosively. This toroidal field instability theory suggests that the internal magnetic geometry is key to the sudden flare, and the flare's magnitude depends on how much energy is stored in these hidden magnetic fields. Some scientists have also explored the possibility that magnetar flares like SGR1806-20 could be connected to external triggers, such as interactions with fallback material, matter left over from the supernova explosion that formed the neutron star. If this material slowly accretes onto the magnetar, it could perturb the magnetic field or crust, acting as a catalyst for an eruption. While less favored than internal magnetic stress models, This idea highlights the complex interplay between a magnetar and its environment, emphasizing that magnetar activity might not be purely internal but influenced by circumstellar matter. Another intriguing but speculative theory involves the role of quantum electrodynamics, QED, effects under the extreme magnetic fields of magnetars. The intense fields can affect the vacuum itself, polarizing it and potentially leading to exotic phenomena like vacuum birefringence or photon splitting. These quantum effects might modulate the way energy is released or trigger instabilities that result in a flare. While this theory is less about the cause of the flare and more about its unique physical characteristics, it offers a glimpse into how magnetars serve as natural laboratories for physics beyond the standard models. Finally, some astrophysicists have proposed that the flare might be related to starquakes that ripple through the magnetar's interior and crust, somewhat analogous to earthquakes on Earth but vastly more energetic and driven by magnetic forces rather than tectonic movement. These starquakes might not only fracture the crust but also excite oscillations or seismic waves within the star, coupling with the magnetic field to amplify the release of energy. The detection of quasi-periodic oscillations in the aftermath of giant flares lends some support to this idea, as it suggests the magnetar's surface and interior were vibrating following the flare. Each of these theories attempts to reconcile the observed energy output, timescales, and spectral characteristics of the SGR1806-20 flare with known physical processes. The reality may involve a combination of these mechanisms, where magnetic stresses, crustal fractures, internal matter phase changes, and magnetosphere dynamics interact in complex ways to trigger such violent outbursts. What is clear is that events like the 2004 giant flare provide invaluable data, pushing the boundaries of astrophysics and challenging our understanding of how matter behaves under the most extreme cosmic conditions. Among the various scientific explanations for the violent eruption of SGR1806-20, the magnetic starquake theory stands out as one of the most compelling and well-supported models. It provides a detailed and physically intuitive framework for understanding how the extraordinary energy release observed in magnetar flares can occur, by drawing a parallel to the geological quakes we are familiar with on Earth, but scaled up to an unimaginably extreme astrophysical context. The fundamental premise of the magnetic starquake theory revolves around the intense stresses imposed by the magnetar's extraordinarily powerful magnetic field on its solid crust. Unlike Earth, whose crust is composed of rock, a neutron star's crust is a rigid lattice made predominantly of neutron-rich nuclei immersed in a sea of degenerate electrons. This crust is incredibly dense and solid but also extremely thin, just about a kilometer thick over a star roughly 20 kilometers in diameter. The internal magnetic field of a magnetar, however, is estimated to be in the order of 10 to the power of 14 to 10 to the power of 15 Gauss, which is trillions of times stronger than the strongest magnetic fields humans have ever created on Earth. These colossal magnetic fields generate immense mechanical stresses on the crust. As the magnetic field lines evolve and twist over time, due to differential rotation or magnetic instabilities, these stresses gradually build up. The crust can only withstand so much tension before it begins to fracture, much like how tectonic plates on Earth eventually slip and cause earthquakes when stress exceeds the frictional forces holding them together. When the crust finally reaches its breaking point, a magnetic starquake occurs. This sudden cracking or shifting of the crust leads to a rapid reconfiguration of the star's magnetic field, causing magnetic field lines to snap and reconnect explosively in the magnetosphere surrounding the neutron star. This process releases a staggering amount of magnetic energy almost instantaneously, producing an intense burst of gamma rays and X-rays, precisely what was observed in the case of SGR1806-20. In the 2004 giant flare from SGR1806-20, the magnetic starquake model suggests that the buildup of internal magnetic stress finally caused a catastrophic fracture in the crust. This fracture would have unleashed energy equivalent to about 10 to the power of 46 ergs in less than a tenth of a second, more energy than the sun emits in 100,000 years, packed into a sudden, searing flash. The quake likely shook the magnetar's surface, sending seismic vibrations rippling through its ultra-dense interior, which may also explain the quasi-periodic oscillations detected in the flare's X-ray tail, interpreted as the star's crust ringing like a bell. The magnetic star quake theory elegantly explains several key observational features of the flare. Firstly, it accounts for the suddenness of the event. Starquakes can occur on very short timescales once critical stresses are reached. Secondly, it explains the enormous energy released, as the magnetic field is capable of storing vast amounts of energy, locked in tension and twisting before the quake. Thirdly, the theory justifies the observed spectral properties of the flare, including the initial hard spike followed by a longer, oscillating tail of softer X-ray emission, as expected from magnetic reconnection and crustal vibrations. Furthermore, the starquake model helps reconcile why magnetar flares are rare and unpredictable. The buildup of magnetic stress and crustal strain is a slow process, potentially taking years or centuries, so flares occur sporadically rather than regularly. This unpredictability adds to the intrigue and challenges of studying magnetars. It also implies that the magnetar's magnetic field is not static but evolves dynamically, continuously reshaping the crust and magnetosphere. The magnetic starquake theory also provides a mechanism for repeated flares, as the crust may fracture multiple times as magnetic stresses rebuild. Smaller bursts observed from SGR1806-20 and other magnetars are often interpreted as minor starquakes or magnetic reconnection events preceding or following a giant flare. Importantly, this theory is grounded in fundamental physics and has predictive power. For example, it suggests that the properties of the crust, its thickness, composition, and elasticity, affect the magnitude and frequency of starquakes. This opens pathways for researchers to use magnetar flare observations to probe the exotic matter properties of neutron star crusts, giving us insights into nuclear physics under extreme conditions inaccessible on Earth. While the magnetic starquake theory is widely accepted, it does not exclude other factors that might contribute to or modify the flare process, such as instabilities in the star's core or magnetospheric dynamics. Nevertheless, it remains the cornerstone explanation for how the energy stored in twisted magnetic fields can suddenly unleash the spectacular bursts observed from magnetars like SGR1806-20. In essence, the magnetic starquake theory paints a dramatic picture of a star under immense internal pressure, where the crust suddenly fractures under magnetic strain, unleashing a cosmic flash of radiation that travels across the galaxy and briefly outshines every other source in the gamma-ray sky. This is the heartbeat of SGR1806-20's flare, a violent, magnetic rupture echoing through space and time. Fast radio bursts, or FRBs, are one of the most puzzling and captivating phenomena in modern astrophysics. These are ultra-brief, ultra-powerful bursts of radio waves that last only milliseconds but carry more energy than our sun emits in days or even weeks. Since their discovery in 2007, FRBs have confounded scientists due to their unpredictability, intensity, and seemingly random origins from far corners of the universe. And yet, among all the mysteries surrounding FRBs, a growing body of evidence is beginning to suggest a compelling connection between these radio flashes and the class of neutron stars known as magnetars, especially those like the infamous SGR1806-20. The hypothesis that magnetars may be the origin of at least some FRBs stems from several overlapping features. Both phenomena involve extreme bursts of energy released in very short timescales. Both are thought to involve highly magnetized environments. And crucially, both defy conventional expectations based on our understanding of stellar evolution and radiation mechanisms. The magnetar connection gained significant traction in 2020, when scientists detected a fast radio burst, FRB200428, coming from a known galactic magnetar, SGR 1935+2154. This was the first time a fast radio burst had ever been linked to a specific, nearby source, and that source happened to be a magnetar. The FRB from SGR 1935+2154 was significantly less energetic than the more distant extragalactic FRBs that had been previously observed, but it was still extraordinarily powerful by galactic standards. Its energy, radio frequency characteristics, and timing all pointed toward a sudden, cataclysmic event in or near the magnetar's magnetosphere. The discovery electrified the astrophysical community, and gave enormous weight to the idea that flaring magnetars might be the missing link in the FRB puzzle. This breakthrough raised an obvious question: could SGR 1806-20, the most powerful magnetar ever detected, have emitted fast radio bursts during its own legendary flare in 2004? Unfortunately, at the time, no instruments were tuned to observe FRBs in conjunction with the flare. The FRB phenomenon itself wasn't even known in 2004, so no effort was made to monitor that part of the radio spectrum. It's possible, perhaps even likely, that SGR 1806-20 emitted a strong burst of radio waves during the flare that simply went undetected. If so, it would serve as yet another bridge between FRBs and magnetars, and might even help explain the true nature of FRBs. To understand how a magnetar might produce an FRB, we must consider the extreme magnetic and plasma dynamics occurring during a flare or magnetic star quake. One popular theoretical mechanism is magnetospheric reconnection. When the magnetic field lines in the outer layers of the magnetar's magnetosphere snap and rearrange, much like solar flares on the Sun but on a vastly larger scale, they can create a shockwave that accelerates electrons to near light speeds. These electrons can then emit coherent radio waves through synchrotron maser emission or other plasma processes, creating the signature spike of a fast radio burst. Another possibility lies in the idea of a sudden ejection of a relativistic plasmid, an expanding ball of charged particles, from the magnetar's surface. As this plasmid interacts with the surrounding magnetic field and ambient plasma, it can generate shock waves that produce a bright, sharp radio pulse. The conditions needed for this kind of emission align almost perfectly with what we know occurs during a magnetar flare: high-energy disruption, rapid acceleration of particles, and the release of pent-up magnetic stress. SGR 1806-20, with its monumental magnetic field and record-breaking flare, represents the most extreme example of a magnetar behaving badly. If any magnetar were to generate a fast radio burst, it would likely be one like this. The fact that we missed detecting a potential FRB in 2004 now serves as motivation for more comprehensive multi-wavelength monitoring of magnetars. In the years since, scientists have developed networks of radio telescopes capable of scanning the skies for FRBs in real time. These include instruments like CHIME in Canada, ASCAP in Australia, and the Meerkat Array in South Africa. These observatories have already recorded hundreds of FRBs, many of which share telltale signs, such as polarization, dispersion, and frequency drift, that hint at highly magnetized environments like those surrounding magnetars. Still, challenges remain. Not all FRBs appear to come from magnetars. Some repeat at irregular intervals, while others appear to be one-off events. Some FRBs show strange modulations or ultra-high brightness temperatures that are difficult to reconcile with even the most extreme magnetar scenarios. This has led some researchers to speculate that multiple mechanisms may be at play in producing FRBs, with magnetars accounting for one class, particularly the repeating or less energetic ones, and other, more exotic mechanisms accounting for the more distant or non-repeating FRBs. Nonetheless, the magnetar connection remains one of the most robust explanations on the table. SGR 1806-20, in particular, serves as a case study in cosmic violence, a natural laboratory for understanding how extreme magnetic environments could give rise to brief, energetic signals across the electromagnetic spectrum. It provides a vivid demonstration of how magnetic energy can be stored, destabilized, and released in ways that boggle the human mind. Looking forward, if we could catch a future flare from SGR 1806-20, or a similar magnetar, with radio observatories actively monitoring the event, we could directly test whether magnetar flares always produce accompanying FRBs. This would not only validate the magnetar FRB hypothesis but also help us decipher the detailed mechanics behind both phenomena. It might also help answer other fundamental questions. Why do some magnetars produce FRBs while others don't? How does the structure of the magnetic field influence the emission? Could the frequency or duration of an FRB provide clues about the magnetar's age, rotation rate, or internal structure? The story of SGR 1806-20 is thus not just a tale of past cosmic fury. It may also be a beacon guiding us toward the future of FRB research. If the secrets of FRBs lie within magnetars, then studying events like the 2004 flare may hold the key to solving one of the most mysterious puzzles in modern astrophysics. What was once a singular, devastating flash of gamma rays might ultimately connect to a broader phenomenon reverberating across the cosmos in radio waves, whispering of distant catastrophes in the magnetic hearts of dying stars. The possibility of Earth being struck by another powerful magnetar flare like the one from SGR 1806-20 is not merely an academic curiosity. It's a real astrophysical concern that has prompted scientific investigation, modeling, and even national preparedness discussions in some countries. While such an event remains extremely rare, the enormous energy these flares can release, even from thousands of light years away, demands that we take the threat seriously, however remote it may seem. To assess the actual danger Earth faces from another magnetar flare, we need to consider several factors: the rarity and distribution of magnetars in our galaxy, the energy required to pose a genuine threat to life or technology on Earth, and our planet's natural protective barriers such as the magnetosphere and atmosphere. Firstly, magnetars themselves are rare. Out of the estimated 100 million neutron stars in the Milky Way, only about 30 have been confirmed as magnetars. These highly magnetized remnants are thought to form under special conditions, most likely from very massive progenitor stars that collapse under their own gravity during a supernova and are born with extreme magnetic fields. Because they evolve rapidly and decay magnetically over time, their active lifespans are relatively short, on the order of 10,000 to 100,000 years, compared to the billions of years that more typical neutron stars may persist. That temporal window for magnetar flaring activity makes the odds of one being dangerously close to us at the exact time of a catastrophic flare quite small. SGR 1806-20, for example, is located about 50,000 light-years away, almost on the opposite side of the galaxy. Even from that distance, its gamma-ray flare briefly affected Earth's upper atmosphere and was detected by multiple space-based observatories. But while it managed to ionize parts of the ionosphere and disrupt some communication frequencies, it caused no significant biological or technological damage. This tells us something very important. In order for a magnetar flare to be truly dangerous, capable of damaging the biosphere or crippling satellites and power grids, it would have to occur considerably closer. Current estimates suggest that a magnetar flare within roughly 10 light-years, or about 60 trillion miles, could be truly catastrophic. Such a proximity, fortunately, is extremely unlikely. The nearest known magnetar to Earth is XTJ 1810-197, which is about 8,000 light-years away. Another well-known one, Swift J 1818.0-1607, is also thousands of light-years distant. No known magnetar lies within the danger zone, and even if there were an undiscovered one nearby, the chances of it erupting at exactly the right moment, and with sufficient intensity, are cosmically small. However, we can't rule out the presence of undetected magnetars entirely. Some may be quiet, not flaring, or obscured by interstellar dust and gas, making them invisible to current instruments. In such cases, it is possible, albeit still improbable, that a nearby magnetar could remain hidden until it suddenly erupts. That said, even quiet magnetars tend to emit soft gamma rays and X-rays periodically or semi-regularly, so with sensitive all-sky surveys like those conducted by the Fermi Gamma Ray Space Telescope and NASA's NICER mission, we are likely to detect any magnetar within a few hundred light-years well before it becomes dangerous. Another layer of defense comes from Earth's magnetic field and atmosphere. High-energy radiation such as X-rays and gamma rays cannot penetrate deep into Earth's surface due to atmospheric absorption. Even if a giant flare were to bathe Earth in radiation, the main damage would occur at high altitudes, affecting satellites, astronaut health, and upper atmospheric chemistry rather than directly irradiating life on the ground. But if the flare were close enough and strong enough, the induced geomagnetic storms could knock out power grids, GPS networks, and radio communications, similar to but more intense than the effects of a solar superstorm. In fact, a magnetar flare hitting Earth would share some similarities with a coronal mass ejection from the Sun, albeit amplified dramatically. It would compress the magnetosphere, induce powerful currents in conductive materials on the ground, and create auroras at lower latitudes than usual. The difference is that while solar storms unfold over hours or days, a magnetar flare would deliver most of its energy in under a second, giving little to no time for reaction or mitigation. The risks also extend to our increasing reliance on space-based infrastructure. Communication satellites, weather satellites, navigation systems, and even manned missions could be at risk if caught unshielded in orbit during a magnetar event. Fortunately, space agencies are already considering such black swan events in their risk models. Agencies like NASA, ESA, and NOAA monitor the skies constantly for high-energy events, and alerts can be issued within seconds when something unusual is detected. There is also some theoretical concern about cumulative exposure. Repeated smaller flares from distant magnetars may contribute to long-term changes in the radiation environment of the solar system, but this remains speculative and poorly constrained. The dominant threat remains a singular, nearby, extremely energetic flare. So, how close would be too close? Current models suggest that a giant flare as powerful as the one from SGR 1806-20 occurring within 10 to 30 light-years could destroy the ozone layer, leading to significant increases in ultraviolet radiation from the Sun reaching the surface, which could in turn trigger mass extinctions. If the source were within 1 light-year, the gamma radiation dose would likely be sufficient to cause direct biological harm to surface life, perhaps even triggering a planetary-scale extinction event similar to the one theorized for a supernova-induced gamma-ray burst. But again, to emphasize, there are no known magnetars within that range, and the odds of one forming there are vanishingly low given our current knowledge of stellar populations in the solar neighborhood. Nearby stars are well mapped, and the kind of massive progenitors required to create a magnetar would be conspicuous in both their past and present forms. In conclusion, Earth is not currently in any immediate danger of being struck by a magnetar flare of catastrophic magnitude. The known magnetars are too far away, and the probability of a hidden, close-by flare-capable magnetar is extraordinarily slim. Nevertheless, as our detection capabilities improve and our understanding of high-energy astrophysics deepens, we remain vigilant. Events like the 2004 flare from SGR 1806-20 serve not just as cosmic curiosities, but as stark reminders of the raw, unpredictable forces that exist in the universe, forces that can, on rare occasions, reach across thousands of light-years to touch our world. What SGR 1806-20 reveals about exotic matter inside neutron stars is one of the most tantalizing frontiers in modern astrophysics. At its core, this is not just a story about violent magnetic storms or high-energy radiation bursts. It's a story about matter pushed to the very limits of physical law. When astronomers study magnetars like SGR 1806-20, they're not merely tracking distant flashes of light. They are, in essence, probing the very heart of atomic structure, testing quantum mechanics, and peering into a regime where matter itself may behave in ways we've never witnessed on Earth. A neutron star is already an exotic object by any standard. It's what remains after a massive star explodes in a supernova, shedding its outer layers and leaving behind a dense core composed almost entirely of neutrons. To put it into perspective, a teaspoon of neutron star material would weigh around 1 billion tons. The pressure inside such a star is immense, so extreme that electrons and protons are literally crushed together to form neutrons, producing a degenerate neutron fluid that resists further collapse through quantum degeneracy pressure. But magnetars like SGR 1806-20 push this model even further. Their immense magnetic fields, up to 10 superscript 1 Gauss, which is trillions of times stronger than anything produced in a laboratory, create conditions in which normal assumptions about matter begin to break down. In such a magnetic environment, even the structure of atoms becomes distorted. Electrons spiral tightly along magnetic field lines, and the atoms themselves can be stretched into long, needle-like configurations. This environment may give rise to states of matter that are not just unfamiliar but fundamentally alien to our current physics. One of the most profound implications of SGR 1806-20 is that it may offer indirect evidence for the existence of exotic matter phases deep inside neutron stars, specifically, forms of matter that go beyond neutrons. These include hyperons, particles containing strange quarks, pion or kaon condensates, and perhaps even deconfined quark matter, where the building blocks of protons and neutrons, quarks, roam freely in a dense, hot soup called quark-gluon plasma. This idea arises in part from how magnetars behave during a flare. The immense energy released during events like the 2004 giant flare from SGR 1806-20 must come from somewhere, and it can't be explained entirely by surface processes. The magnetic field rearrangements that cause the flares must originate from deep within the crust or core of the star, implying internal stress mechanisms far beyond what can be accounted for by conventional nuclear matter. These stress mechanisms may involve phase transitions of matter at ultra-high densities, precisely the kind of behavior that exotic matter theories predict. One hypothesis is that under such intense magnetic and gravitational pressure, the neutrons themselves may melt into their constituent quarks, forming a quark matter core. This state, called strange quark matter if it contains strange quarks, is theorized to be even more stable than normal nuclear matter under certain conditions. If such a core exists, then internal magnetic stress might propagate differently, perhaps faster or with more energy, triggering more violent and unpredictable surface events like those seen in SGR 1806-20. Some models even suggest that part of the internal magnetic field in magnetars could be frozen into a superconducting, superfluid mixture of quarks and leptons. This would not only allow for immense storage of magnetic energy, but also unique oscillatory modes that could match the quasi-periodic oscillations (QPOs) observed after some magnetar flares. These QPOs, rhythmic pulses in X-ray brightness following the initial flare, may act as seismic waves, rippling through the star, offering rare insight into its internal composition, much like seismology reveals the Earth's interior. SGR 1806-20's flare, among the most powerful cosmic events ever recorded in our solar system's vicinity, showed such QPOs. This is significant because these oscillations hint at the rigidity and elasticity of the star's crust and core, properties that depend heavily on what kind of matter lies within. If the crust can crack and rebound with measurable frequency, it suggests a structure that is perhaps composed of nuclear pasta, a theorized phase of matter where nucleons form bizarre shapes such as rods, sheets, and spirals due to the extreme forces acting on them. These structures may lie between the outer crust and the inner core, acting as a buffer between traditional neutron-rich matter and potentially more exotic substances within. Furthermore, the ability of SGR 1806-20 to release such a colossal amount of energy so suddenly also raises questions about how energy is stored and transferred inside a magnetar. If standard models of neutron star matter fall short in explaining this efficiency, then exotic matter, whether in the form of hyperons, Bose-Einstein condensates, or quark matter, might offer a solution. These states could allow for higher energy densities or more elastic energy storage, resulting in more violent releases when the magnetic field lines untangle or reconnect. Another tantalizing possibility is that SGR 1806-20 might be in a transitional phase, a kind of intermediate state between a neutron star and a black hole. If the core is made of quark matter or some yet unknown exotic state, it may eventually collapse into a black hole, releasing tremendous gravitational and electromagnetic energy in the process. The flare observed in 2004 might have been a precursor to such a collapse, though clearly not the final act, as SGR 1806-20 still exists and continues to be monitored. In this light, magnetars like SGR 1806-20 function almost as natural laboratories for studying quantum chromodynamics, QCD, the theory of the strong nuclear force, under conditions that are impossible to replicate on Earth. The behavior of matter at these densities and field strengths provides crucial data for refining our understanding of how the universe behaves at its most extreme scales. In fact, some physicists have even proposed using SGR 1806-20 and similar magnetars to test theories of quantum gravity or extradimensional physics. The notion is that the immense gravitational and magnetic fields in and around the magnetar may cause deviations from Einstein's general relativity, if only we had instruments sensitive enough to detect them. Such a breakthrough could potentially revolutionize our understanding of space-time itself. So, When we observe the lingering X-ray afterglows, the pulse patterns, and the sudden energy releases of SGR 1806-20, we are not just watching a star behave violently. We are catching a glimpse into an utterly alien world, where atoms are warped by magnetic lines, where quarks may roam free in searing plasma, and where the structure of matter itself becomes a mystery. In many ways, SGR 1806-20 is not just an astronomical object, it is a key, a portal, through which we might one day unlock the true nature of matter, energy, and perhaps even the birthplaces of black holes. One of the more intriguing and provocative questions about SGR 1806-20 lies in the possibility that it may not just be an exceptionally active magnetar, but potentially an early or transitional form of a black hole. While the idea might seem speculative at first glance, it is grounded in a series of observational clues and theoretical frameworks that suggest certain magnetars, particularly the most extreme ones like SGR 1806-20, could be part of a short-lived evolutionary window before gravitational collapse into a black hole occurs. To understand how this might be possible, we have to start with what defines the line between a neutron star and a black hole. Neutron stars form from the collapsed cores of massive stars after a supernova explosion. If the remnant mass after collapse is below a certain limit, commonly estimated to be around 2.2 to 2.4 solar masses, though this figure is still debated, it stabilizes as a neutron star. If it exceeds that limit, it collapses further into a black hole. Now, magnetars are neutron stars with magnetic fields so powerful, on the order of 10 superscript 1 to 10 superscript 1 Gauss, that they can dramatically affect the structure and behavior of the star. Their extreme magnetic fields not only distort the matter within the star but also produce outward magnetic pressure, effectively working against gravitational collapse. In other words, the internal magnetic forces might be temporarily propping up the magnetar, allowing it to exist in a precarious balance just below the threshold for black hole formation. This gives rise to the tantalizing idea that SGR 1806-20 may be sitting right on that razor's edge. Its mass could be uncomfortably close to the Tolman, Oppenheimer, Volkoff, TOV limit, the theoretical maximum mass a neutron star can have before collapsing under its own gravity. If so, then any significant loss of support, such as decay of the magnetic field, internal matter rearrangement, or an abrupt phase transition inside the core, could trigger its rapid transformation into a black hole. There's another reason to consider this possibility: energy output. The flare emitted by SGR 1806-20 in 2004 was so powerful, releasing more energy in 1/10 of a second than the Sun emits in 100,000 years, that it may signal a deep internal instability. In many black hole formation models, a final energy outburst precedes the collapse. While no definitive evidence suggests that SGR 1806-20 has already collapsed, the scale and suddenness of that flare suggests the kind of massive rearrangement of internal structure that might foreshadow a gravitational implosion. This speculative path, of a magnetar transitioning into a black hole, has found traction in theoretical astrophysics circles. In fact, some researchers propose that the end stages of magnetars may follow a unique route to black hole formation, distinct from standard neutron star collapse. Rather than collapsing solely due to accumulating mass, a magnetar could collapse due to magnetic energy depletion. Over time, as magnetic reconnection events, like giant flares, bleed off energy, the structural support weakens. Eventually, the intense gravity overcomes the remaining degeneracy and magnetic pressure, resulting in a sudden and catastrophic collapse into a singularity. In this context, SGR 1806-20 may be undergoing its pre-collapse turbulence, releasing enormous amounts of magnetic energy as it spirals toward its gravitational fate. This would make it one of the rarest and most valuable objects in the cosmos, a real-time demonstration of stellar evolution in its final, violent stage. Adding further weight to this idea is the existence of hybrid models, theoretical objects that begin as magnetars and evolve into black holes not instantaneously, but gradually. In these models, the magnetic field decays over thousands to millions of years, and the internal composition of the star shifts. As the pressure equilibrium breaks down, the core might begin collapsing before the crust does, leading to exotic transitional states like metastable quark cores or gravitational instabilities detectable through gravitational waves. If such processes exist, SGR 1806-20 may already be exhibiting signs of that decay. There's also a speculative twist involving the nature of quark deconfinement. If the core of SGR 1806-20 already contains deconfined quark matter or a strange quark phase, then the system might be on a pathway that naturally ends in collapse. In these models, once a critical density is achieved, the inner core collapses into a black hole, while the outer shell of the star momentarily resists, creating a time window where bizarre interactions occur, perhaps resulting in flares, gravitational wave signatures, or other emissions that precede the final blackout. This offers a wild but intriguing possibility. The flare from 2004 might have been not just a magnetic quake or crustal fracture, but the early tremor of gravitational collapse, a death cry from a star that's now slowly vanishing into oblivion. Of course, this theory is difficult to prove observationally. Once a neutron star collapses into a black hole, it effectively disappears behind an event horizon, cutting off any further electromagnetic communication. But there are hints that astrophysicists can look for. One is a sudden drop in pulsed emissions. If a magnetar like SGR 1806-20 were to suddenly vanish from the X-ray sky without leaving a supernova remnant or any secondary signals, that might indicate a silent collapse into a black hole. Similarly, gravitational wave observatories like LIGO and Virgo could, in the future, detect the ripples of such an internal collapse, giving humanity its first indirect proof that magnetars can indeed become black holes. Another fascinating implication of this hypothesis is what it means for black hole formation rates in the universe. If magnetars can serve as precursors or transitional objects on their way to black holes, then the cosmic census of black holes may be more tightly coupled to magnetar populations than previously thought. And since only a fraction of neutron stars become magnetars, we might now be looking at a small, elite class of stars that act as delayed black hole progenitors. In short, SGR 1806-20 may not only be the most extreme magnetar ever observed, but also one of the most ephemeral. It may represent a window into a rare evolutionary phase of stellar death that bridges the chasm between neutron star and black hole. And if that's true, then every pulse, every flare, and every quaking echo it sends across the cosmos may be a fleeting message from a dying giant, speaking the final language of matter before falling into eternal silence. When comparing the energy released by SGR 1806-20 to other cosmic explosions throughout the history of our universe, it becomes clear just how extraordinary this event truly was. Although not the most energetic cosmic event ever observed, it remains one of the most powerful non-destructive bursts of energy to reach Earth in recorded scientific history. To fully appreciate the scale and uniqueness of SGR 1806-20's 2004 flare, we must place it against a backdrop of other astronomical phenomena, from supernovae and hypernovae to gamma-ray bursts, and even theoretical cosmic events like white hole emissions or primordial black hole evaporations. The December 27, 2004 flare from SGR 1806-20 released more energy in 0.1 seconds than the Sun produces in 100,000 years. That amounts to roughly 10 to the power of 46 ergs, or about 10 to the power of 39 joules of energy, an explosion so powerful that if it had occurred within 10 light-years of Earth, it could have destroyed our ozone layer or worse. Yet, SGR 1806-20 is 50,000 light-years away, in the constellation Sagittarius, and still, its effect was measurable on Earth. That's how absurdly energetic it was. For comparison, consider a typical supernova, which releases about 10 to the power of 51 ergs of energy. That's about 100,000 times more energy than the SGR 1806-20 flare, but the difference is in delivery. A supernova releases that energy over a period of days or even weeks and in all directions. Meanwhile, the SGR 1806-20 flare released a much smaller amount of energy, but concentrated it in less than a second, and likely in a focus beam, which makes its fluence, energy per unit area, far more intense for any observer in the path. So while the total energy was less, the intensity of radiation per second per square centimeter that reached Earth was staggering. It briefly became the brightest known source of gamma rays in the sky, outshining everything else outside our solar system. Next, compare it to gamma ray bursts, GRBs, the most powerful known explosions since the Big Bang. A long-duration GRB can emit more than 10 to the power of 53 ergs of energy, often believed to be the death throes of massive stars collapsing into black holes or the merger of neutron stars. GRBs are rarer, more collimated, focused like a laser, and far more distant. Yet, most GRBs we detect are so far away that their actual effect on Earth is minimal despite their insane power. The SGR-1806-20 flare, by contrast, was much closer and still extremely intense, even if it wasn't in the GRB category of raw energy output. In fact, some scientists initially thought the SGR-1806-20 flare was a short GRB, because its energy signature matched the characteristics of a short hard gamma ray burst. It was only the secondary pulses and known location of the magnetar that confirmed it was a galactic source, a magnetar flare, not a cosmological GRB. This overlap in appearance between GRBs and magnetar flares has led to speculation that some fraction of short GRBs might actually be extragalactic magnetar flares occurring in distant galaxies. In that sense, SGR-1806-20 may not only rival GRBs in intensity but also masquerade as one. Even more impressively, if we compare it to the famous Carrington event, the 1859 solar storm that disrupted telegraphs and lit up the skies with auroras as far as the tropics, the SGR-1806-20 flare dwarfs it in energy. The Carrington event, while impressive by solar standards, was a mild whisper compared to the thunderous shout of this magnetar flare. Yet it caused global technological disturbance. The fact that SGR-1806-20's burst didn't do the same is only because of its distance. Going further into cosmic history, some events reach energies that utterly eclipse SGR-1806-20 in total magnitude, but again, distance and intensity per second per square centimeter are key. The Big Bang, for instance, is estimated to have released 10 to the power of 69 joules in its first moments, a number so vast it strains comprehension. Hypernovae, often seen as long-duration GRBs resulting from the collapse of stars over 100 times the mass of the Sun, can release up to 10 to the power of 54 ergs. Yet none of these have ever sent energy directly to Earth at a level that triggered ionospheric disruption in real time. SGR-1806-20 did. What about quasar outbursts? These are powerful emissions from the supermassive black holes at the centers of galaxies. While quasars are some of the most luminous objects in the universe, their energy is spread out across enormous distances and time scales, millions of years. Even the most powerful quasar doesn't pack the punch in a split second the way SGR-1806-20 did. That's what makes magnetars so interesting. They are not as large or long-lasting as quasars or black holes, but they produce short, localized, catastrophic eruptions of concentrated energy that are uniquely dangerous. Then there's the category of theoretical exotic events. For instance, if a primordial black hole evaporated via Hawking radiation, it could potentially release 10 to the power of 30 to 10 to the power of 40 joules in its final moments, again in a flash that might resemble a gamma ray burst. But no such evaporation has yet been observed. SGR-1806-20, in contrast, is real, measured, and terrifyingly close by cosmic standards. It's also useful to consider historical observations. Before the 2004 flare, astronomers had never recorded such a bright, nearby high-energy burst. The previous two most significant soft gamma repeater flares, one from SGR 1900+14 in 1998 and another from SGR 0526-66 in 1979, were powerful but not nearly as intense. The SGR 0526-66 burst, for instance, occurred in the Large Magellanic Cloud about 160,000 light-years away and still triggered major alerts on Earth. But its fluence was dwarfed by SGR 1806-20, which, despite being over 50,000 light-years away, saturated sensors and ionized Earth's upper atmosphere. Even among magnetars, SGR 1806-20 stands out. Most emit X-rays and soft gamma rays intermittently, but this event wasn't just a flare, it was a cosmic detonation. For astronomers, it remains a benchmark, the gold standard against which other magnetar flares are measured. Every subsequent magnetar discovery is compared to SGR 1806-20 in terms of magnetic field strength, flare energy, and proximity to Earth. In short, while there have been more energetic events in terms of raw output, very few have matched the combination of proximity, intensity, and concentration of energy that made SGR 1806-20's flare so remarkable. It didn't just unleash unimaginable power, it directed it across space in a burst of cosmic violence that, for a fraction of a second, reminded Earth of the immense and uncontrollable forces that lie scattered across our galaxy. What truly elevates SGR 1806-20 to the status of the most powerful known magnetar isn't just a single quality. It's the staggering combination of extreme properties working in tandem, culminating in one of the most explosive celestial events humanity has ever observed. At the intersection of density, magnetism, rotational dynamics, and sheer unleashed energy, SGR 1806-20 does not just check all the boxes for being extreme, it rewrites the scale entirely. Let's begin with its classification. SGR 1806-20 is part of a rare family of neutron stars known as soft gamma repeaters, or SGRs. These are magnetars that emit unpredictable bursts of soft gamma rays and X-rays, a phenomenon linked to the immense stresses generated by their ultra-powerful magnetic fields. Among SGRs, SGR 1806-20 reigns supreme, not only for the singularly violent flare it produced on December 27, 2004, but for the overall strength of its magnetic field and its highly dynamic behavior. The magnetic field of SGR 1806-20 is estimated to be around 2 times 10 superscript 1 Gauss. To understand just how absurdly powerful that is, consider that Earth's magnetic field is around 0.5 Gauss. This means the magnetic field of SGR 1806-20 is 4 quadrillion times stronger than Earth's. In fact, if SGR 1806-20 were located just 1,000 kilometers away from Earth, a distance relatively short in space, it could strip the information off every credit card on the planet and potentially disintegrate all electronic devices due to the raw magnetic force alone. Fortunately, it lies 50,000 light-years away. But this demonstrates how raw magnetic violence defines its very nature. Beyond the magnetism, there's the sheer mass and density of the object. Like all neutron stars, SGR 1806-20 is the collapsed core of a massive star, compressed into a sphere only about 20 kilometers, 12 miles, in diameter. That's roughly the size of a city. Yet it contains more mass than the Sun. Imagine squeezing the mass of 1.4 solar masses into a space the size of Manhattan, and you start to appreciate the internal pressure and strain on its structure. The matter inside is in an exotic, degenerate state that is still not entirely understood, possibly involving hyperons, quark matter, or other exotic particles not observed under normal conditions. It's this immense internal stress that contributes to the instability we observe on the surface. Then, there is the rotational energy. Although SGR 1806-20 is slowing down due to the intense magnetic braking caused by its field, it still rotates once every 7.5 seconds. While that may sound slow compared to millisecond pulsars, it is remarkably fast considering the magnetar's other features. The rotation further twists and distorts the magnetic field, which in turn creates tectonic-like stresses in the ultra-dense crust of the star. When these stresses snap, just as tectonic plates do on Earth, they unleash violent bursts of electromagnetic radiation, known as magnetic star quakes. The 2004 event was one such quake, but magnified to apocalyptic levels. So, what exactly happened during that infamous flare? In that moment, SGR 1806-20 released approximately 10 to the power of 46 ergs of energy, the equivalent of more than 100 trillion nuclear bombs detonating simultaneously. This was more energy than the Sun emits in 100,000 years, discharged in a tenth of a second. It was so powerful that it actually saturated multiple spacecraft sensors and ionized Earth's upper atmosphere, causing disruptions in long-range radio signals despite being located tens of thousands of light-years away. What's important to understand is that other magnetars have also produced flares. SGR-0526-66 in 1979 and SGR-1900+14 in 1998, for example, but none have matched the sheer peak brightness or radiation fluence of the 2004 event. Some were energetic, but not close enough to Earth to rival its impact. Others may have been closer, but did not unleash the same magnitude of energy. Only SGR-1806-20 holds the unique distinction of being both unimaginably violent and close enough to Earth to be detected with such clarity and intensity. Another striking feature of SGR-1806-20 is how its flare altered the surrounding environment. Observations revealed that the star's magnetosphere, its extended magnetic atmosphere, was twisted and reconfigured by the flare, releasing energy and particles in complex patterns. Post-flare monitoring showed significant changes in its X-ray emission profile, suggesting that the magnetar's crust and magnetic field had been fundamentally altered by the quake. It was as if the magnetar suffered a cosmic-scale seizure, releasing centuries of pent-up magnetic stress in a moment of violent release. Its location in our galaxy also adds to the intrigue. SGR-1806-20 is part of a stellar cluster known as CL*1806-20, which includes some of the most massive and luminous stars in the Milky Way, such as the famous blue hypergiant LBV 1806-20. This crowded stellar nursery is a natural breeding ground for massive stars that live fast and die young, often collapsing into black holes or neutron stars. That SGR-1806-20 emerged from such a place isn't surprising, but that it became so intense and volatile speaks to either the extreme conditions of its birth or perhaps the influence of nearby massive stars and gravitational interactions over time. All these factors, the extreme magnetic field, compact mass, rapid rotation, exotic internal matter, seismic starquakes, and location within an energetic stellar nursery, combined to make SGR-1806-20 a singular beast. But it was the flare itself, recorded and analyzed globally, that truly cemented its title as the most powerful magnetar ever observed. No other magnetar, pulsar, or neutron star has produced a burst that affected Earth's atmosphere from across half the galaxy. That alone makes SGR-1806-20 not just the most extreme known magnetar, but one of the most significant astrophysical phenomena in modern observational history. Its legacy goes beyond numbers. It serves as a cautionary tale about the latent violence in the cosmos, a reminder that small, dense, hidden objects can unleash devastation on scales that rival supernovae, even without exploding entirely. The question now lingers in every astrophysicist's mind: if this happened from 50,000 light-years away, what would a similar flare from a closer magnetar do to Earth? In the cosmic theater of destruction, supernovae are often hailed as the ultimate acts, cataclysmic finales that end the lives of massive stars in a blaze of glory. These explosions can outshine entire galaxies for brief periods, dispersing elements forged in stellar cores into the interstellar medium, seeding the universe with the raw materials for future stars, planets, and possibly life itself. For decades, they've been the gold standard for astronomical violence. Yet, standing beside them, albeit often overlooked due to their rarity and stealthier signatures, are the magnetar flares, especially the monstrous eruption of SGR-1806-20. Though it lacks the prolonged brightness or the visible shell of ejected material that characterizes a classic supernova, SGR-1806-20's flare, in terms of instantaneous power and impact, challenges even the grandeur of a star's death. Comparing these two phenomena reveals not just their differences, but how nature offers multiple flavors of apocalypse. Let us start with the sheer scale of energy. A typical supernova releases about 10 to the power of 51 ergs of energy. This is spread out over the course of several days or weeks, depending on the type. A Type 2 supernova, for instance, caused by the core collapse of a massive star, radiates much of its energy in the form of neutrinos, with only a small portion becoming visible light or kinetic energy that propels stellar debris into surrounding space. In contrast, the flare from SGR-1806-20 was much shorter, releasing approximately 10 to the power of 46 ergs in just 0.1 seconds. On paper, this looks like a 5 order of magnitude difference in favor of the supernova. But context is crucial. The magnetar flare's power output, defined as energy per unit time, was on a completely different level. SGR1806-20's flare had a luminosity of about 10 to the power of 47 ergs per second, far greater than the peak luminosity of a typical supernova, which is often around 10 to the power of 43 to 10 to the power of 44 ergs per second. In that brief tenth of a second, SGR1806-20 outshone almost every other event in the galaxy. If we were to compress the entire energy of a supernova into a similar timescale, we'd be dealing with something approaching the theoretical energy release of a gamma-ray burst, which magnetar flares are sometimes compared to. But most supernovae are drawn-out affairs. They flash brightly in visible light and fade slowly, their total energy diffused and diluted over time. The magnetar flare was a pulse, a snap of cosmic fingers that screamed with energy and then vanished into darkness. Another key difference lies in their physical mechanisms. Supernovae are born when a star can no longer resist gravity. When nuclear fusion in the core ceases, there's nothing to counteract the immense inward pull of the star's own mass. The core collapses, the outer layers rebound or are blasted away, and what's left behind is often a neutron star, or if the mass is great enough, a black hole. The violence is intrinsic to the structure of the star tearing itself apart. Magnetar flares, however, are not about death but stress. A magnetar like SGR1806-20 is already the remnant of a supernova, a neutron star stabilized by the degeneracy pressure of neutrons and bound by crushing gravity. Its destruction has already occurred, and what we observe is a kind of aftershock, a symptom of the extreme conditions festering in this leftover core. Its magnetic field, contorted by internal motions and strained by crustal shifts, builds tension until it snaps, like a spring suddenly released after being twisted far beyond its limits. The flare is the consequence of that sudden magnetic realignment and crustal cracking, resulting in an electromagnetic outburst of incredible magnitude. From an observational standpoint, supernovae are majestic and visible, often appearing in telescopes as bright, expanding clouds of gas. They provide astronomers with clues about star formation, galaxy evolution, and element creation. Magnetar flares, on the other hand, are almost ghost-like. They don't light up the sky in the traditional sense. Their energy comes primarily in the form of X-rays and gamma rays, invisible to the naked eye and only detectable by specialized space-based instruments. Yet, the impact can be far more immediate and focused. Whereas a supernova disperses its energy omnidirectionally and gradually, the flare from SGR1806-20 was tightly concentrated in electromagnetic radiation, blasting outwards at near light speed and hitting Earth with enough power to disturb its ionosphere, despite originating 50,000 light-years away. If a typical supernova occurred at the same distance, Earth would mostly observe it as a bright point in the sky. Depending on its proximity and type, it might even be visible in daylight, like SN 1054, which created the Crab Nebula. But it wouldn't immediately harm our planet unless it occurred within a few dozen light-years. A magnetar flare like that of SGR1806-20, however, because of its intensity and the nature of the radiation it emits, could pose a direct threat even from significantly farther distances. Soft gamma rays and hard X-rays can strip away planetary atmospheres, destroy ozone layers, and initiate mass extinction-level biological effects, particularly if the burst is directed straight at Earth. There's also the predictability factor. Supernovae, though rare, are easier to anticipate in some respects. We can identify massive stars nearing the end of their lives, such as Betelgeuse, and monitor them for signs of imminent collapse. Magnetars are less cooperative. Their flares are sudden and without consistent warning. One moment, a quiet neutron star; the next, a crack in the crust unleashes a planetary-scale electromagnetic scream. In terms of destructive potential to Earth, both events are dangerous, but in different ways. A supernova would need to be within 30 light-years or so to significantly threaten Earth's biosphere via radiation. A magnetar flare like SGR1806-20, though less energetic overall, could potentially cause serious biological and atmospheric damage from a distance of a few thousand light-years, especially if Earth were directly in the line of fire of its gamma-ray beam. One of the reasons SGR 1806-20 remains so iconic is not just because of its raw power, but because it reminded scientists that you don't need an entire star to explode to witness a cosmically dangerous event. A single, compact neutron star, barely 20 kilometers in diameter, could produce a flare potent enough to be detected across half the Milky Way, affect Earth's ionosphere, and send our communications satellites scrambling. That's an entirely different kind of fear, one born from subtlety and silence, from an object so small and dark it is invisible to most observers, and yet capable of instantaneous destruction on planetary scales. We often imagine cosmic apocalypse in terms of massive explosions and blinding light. But SGR 1806-20 teaches a subtler lesson, that there is terror in compression, in magnetic tension, in extreme forces that don't explode, but instead snap, invisibly, violently, and without warning. So, while the total energy output of a magnetar flare may be dwarfed by a supernova on paper, in practical terms, its delivery method, intensity, and targeted radiation make it one of the most concentrated threats in the known universe. It is the difference between a bomb detonating miles away and a laser burning through a single point instantly. One is broader in scope, the other is sharper, more surgical, and arguably more terrifying. In the grand cosmic hierarchy of explosive phenomena, then, SGR 1806-20 does not dethrone the supernova, but it redefines what destructive power can look like. The most powerful known magnetar flare didn't rival a star's death in total energy. Instead, it distilled the essence of destruction into a single, precise moment, proving that sometimes, the most dangerous forces are not the loudest or largest, but the ones that wait silently, wound-tight with tension, until the moment they erupt. In the earliest hours of December 27, 2004, a subtle but colossal event unfolded in the deep vacuum of space. At first, there was no sign anything had occurred. The skies above Earth were quiet. No bright supernova bloomed in the night, no visible disruption altered the familiar canvas of stars. But far above the planet's surface, in the silent watch of orbit, a chorus of instruments began to scream. The initial indication came not from a telescope, but from orbiting gamma-ray detectors. NASA's Rossi X-ray Timing Explorer, RXT, the International Gamma-ray Astrophysics Laboratory, Integral, and the Swift Gamma-ray Burst mission, along with several other spacecraft, suddenly registered a colossal spike in high-energy radiation. Simultaneously, detectors aboard RESI, Reuven Ramadi High-Energy Solar Spectroscopic Imager, a spacecraft intended to study solar flares, were overwhelmed by a flash of gamma rays so intense that, for a moment, it saturated their sensors. Wind, Cluster, and Geotail, three other satellites positioned across different points in Earth orbit, picked up the same event within milliseconds of each other. Across the planet, observatories scrambled to make sense of what had just hit the spaceborne instruments like a hammer. The pulse had come with no warning, no precursor event, no gradual buildup. Instead, it struck suddenly and with a ferocity that left instruments stunned. Some gamma-ray detectors that were not even pointed toward the event still registered it, as the radiation scattered off the Moon, Earth's atmosphere, or other satellites, creating echoes and false positives that initially confused data analysts. But once they synchronized the timestamps from different observatories, the picture became alarmingly clear. Something had unleashed one of the most powerful outbursts of electromagnetic energy ever recorded within the Milky Way. What followed was a frantic attempt to triangulate the source. Given the different arrival times of the pulse at various satellites, each stationed at different points in orbit or at different distances from Earth, scientists could calculate a time delay triangle. This method works by comparing the exact moment the gamma rays hit each satellite and computing the direction they must have originated from based on those discrepancies. It's not unlike how GPS works in reverse, using timing to find a position in the sky. This triangulation pinpointed the source of the gamma-ray burst to a region within the constellation Sagittarius, specifically, to a known magnetar designated SGR 1806-20, located within a star-forming region near the galactic plane approximately 50,000 light-years from Earth. The name, SGR, refers to its classification as a soft gamma repeater, a rare class of magnetars known for sporadic bursts of gamma rays and X-rays, often associated with sudden magnetic or crustal shifts. SGR 1806-20 had already been catalogued as a potential threat, its previous bursts having been mild by comparison, but nothing had prepared scientists for the magnitude of this flare. The detection wasn't limited to satellites either. Ground-based observatories noticed something peculiar as well. Earth's ionosphere, the layer of the upper atmosphere responsible for reflecting and modulating radio waves, reacted sharply to the incoming gamma radiation. Normally stable at that hour, the ionosphere abruptly changed in composition and density, a clear sign that high-energy radiation had interacted with it. This kind of global disturbance typically only occurs during massive solar flares. Yet no activity was coming from the Sun. The source had to be something else, something far beyond our solar system. One of the most striking details about this flare was the sheer intensity of its initial spike, referred to as the initial pulse. This pulse lasted just 0.2 seconds, yet in that moment it delivered as much energy to Earth as would be received from the full moon over an extended period. That might not sound dramatic until you consider this. The full moon is a constant source of reflected solar light, and this burst matched that brightness, not in visible light but in high-energy radiation, in a fraction of a second. For a brief instant, SGR 1806-20 outshone every object in the sky in the gamma-ray spectrum, despite being 50,000 light-years away. The only reason Earth wasn't scorched was because the flare, though immensely powerful, was dispersed over vast distances and likely only partially directed toward us. Following the initial pulse, a tail of radiation followed, lasting several minutes. This afterglow was less intense but still potent, and it gave scientists a rare opportunity to study the behavior of a magnetar after a major flare. Instruments that had been temporarily overloaded by the initial spike recovered in time to capture this lingering signal, offering clues about the mechanisms at play within the magnetar's crust and magnetic field. NASA's RESI, for instance, recorded oscillations in the X-ray signal during the tail that hinted at star quakes, vibrational reverberations of the neutron star's crust, ringing like a struck bell after the initial rupture. The scale of global detection also led to collaboration across international boundaries. Scientists from the United States, Europe, Japan, and Russia compared data from over a dozen spacecraft. Even satellites whose primary missions had nothing to do with astrophysics, like those designed to monitor nuclear weapon tests, such as those used by the U.S. Department of Defense, recorded the event. This cross-disciplinary confirmation underscored the power and reach of the flare. Something so distant had managed to touch almost every tool humans had floating in space. What was perhaps even more remarkable was how lucky Earth had been. If SGR 1806-20 had been significantly closer, say, within 10,000 light-years, the event could have done more than just disturb the ionosphere. It could have crippled satellites, disrupted radio communication, and even, in worst-case theoretical models, affected the biosphere. Yet because of its distance, and the fact that only a fraction of its beam intersected Earth, we were left with an unprecedented scientific opportunity rather than a catastrophe. For astronomers, detecting SGR 1806-20's flare was a once-in-a-lifetime event. It was the most powerful burst of gamma radiation detected from within our galaxy, and it became a reference point for all future studies on magnetars, flares, and high-energy astrophysics. It also acted as a calibration point for satellite sensors. Many instruments that had never recorded such high readings before were tested to their limits, leading to a re-evaluation of safety protocols, sensitivity ranges, and data analysis methods. The detection of this flare also changed the way scientists thought about gamma-ray bursts, GRBs. For decades, GRBs had been associated primarily with distant, extragalactic sources, massive explosions billions of light-years away. But the SGR 1806-20 event showed that magnetar flares could mimic short-duration GRBs, especially if the flare's initial pulse is observed from a distance, and the tail is missed due to the observational angle. This realization led to a hypothesis that a small but significant fraction of previously catalogued short GRBs might actually be magnetar flares in nearby galaxies. Thus, the flare from SGR 1806-20 wasn't just detected, it was experienced by the instruments circling Earth. It was a wake-up call, a whisper of raw cosmic power that reached across the galaxy and rang alarms in every high-energy detector humanity had deployed. And in that moment, we understood something profound. Even the remnants of stars, long after their supernova deaths, could still shake the very fabric of our planetary environment. In the ever-unfolding chronicle of cosmic discovery, the flare from SGR 1806-20 on December 27, 2004, occupies a position of immense historical significance, particularly in the specialized realm of gamma-ray astronomy. While it was far from being the first gamma-ray event ever recorded, it marked a transformative moment that forever reshaped how scientists perceived the nature, variety, and impact of high-energy phenomena in our galaxy. Before this flare, magnetars were already fascinating objects, rare neutron stars with magnetic fields so intense that they defied conventional physics. But SGR 1806-20 took everything previously theorized about these stellar remnants and elevated it to an almost mythic reality. The historical gravity of this event begins with its raw power. Prior to 2004, the most powerful gamma-ray bursts, GRBs, had always been associated with extremely distant galaxies, cataclysmic explosions occurring billions of light-years away. These were seen as exotic phenomena, long-duration GRBs from collapsing massive stars forming black holes, and short-duration GRBs likely from neutron star mergers. But SGR 1806-20 redefined that boundary. For the first time, astronomers saw an event with comparable gamma-ray luminosity emerge from within our own Milky Way, shattering the previous assumption that such explosive outputs could only originate from distant cosmological sources. And yet, what made SGR 1806-20 so revolutionary wasn't merely its intensity. It was the proximity and clarity of its signature. When the flare erupted, it instantly became the brightest extrasolar event ever observed in the gamma-ray spectrum. Instruments around Earth were temporarily saturated. Even devices not designed for gamma-ray detection recorded anomalous readings. The event served as an accidental calibration point for a wide range of high-energy observatories, some of which had never been exposed to that level of intensity before. As a result, data collected from SGR 1806-20 became a benchmark, a reference that would guide the development, testing, and tuning of gamma-ray and X-ray detection systems for years to come. From a historical standpoint, SGR 1806-20 also forced a reevaluation of the soft gamma repeater (SGR) classification. Prior to this flare, SGRs were a somewhat niche subclass within gamma-ray astronomy. They were known for emitting erratic, soft gamma-ray bursts and were already suspected to be magnetars, but there remained debate regarding their full energetic potential. This single event erased all doubt. SGR 1806-20 confirmed beyond question that magnetars could not only produce localized bursts but could erupt with enough force to rival, and in some ways, exceed, the energy output of distant GRBs. Suddenly, SGRs were no longer just peculiar emitters. They were among the most explosive natural phenomena in the known universe. Historically, it also demonstrated something scientists had speculated about but never directly observed, that a magnetar's magnetic field alone, absent any traditional fuel like nuclear fusion or accretion, could drive an explosion of catastrophic magnitude. This introduced a new category of astrophysical violence into the scientific record, magnetically powered explosions. Where traditional supernovae derive energy from the collapse of massive stellar cores, and GRBs from relativistic jets, SGR 1806-20 represented a fundamentally different type of power source, one grounded in the sudden release of magnetic energy from deep within the neutron star's crust. It was a dramatic confirmation of theoretical predictions that had long gone unproven. In the late 20th century, theoretical astrophysicists had speculated that magnetic fields in some neutron stars could reach or even exceed 10 superscript 1 Gauss, over a quadrillion times stronger than Earth's magnetic field. But it wasn't until SGR 1806-20's flare that the implications of such magnetism were made viscerally real. This was no longer just speculation scribbled into research papers. It was an empirical reality that shook the very sensors of humanity's space-based observatories. Furthermore, the flare catalyzed a new approach to multi-instrument and multi-wavelength coordination. The event was so extreme, and so widely detected, that it essentially forced international and interagency cooperation on an unprecedented level. NASA, ESA, JAXA, and several defense satellite networks cross-referenced their findings, leading to rapid publications and joint press releases. In a way, SGR 1806-20 was one of the first global astrophysical events that necessitated the modern era of collaborative astronomy. The coordinated effort not only ensured a more complete understanding of the event but also laid the groundwork for protocols that would later be used in the detection of gravitational waves and other multi-messenger astrophysical phenomena. It also taught researchers to reconsider the identities of previously detected short gamma-ray bursts, SGRBs. Prior to 2004, many short-duration gamma-ray events were assumed to be extragalactic, typically associated with neutron star mergers or other relativistic phenomena. But after studying the characteristics of the SGR 1806-20 flare, particularly its incredibly short, intense initial spike followed by a softer extended tail, astronomers realized that magnetar flares could mimic the signature of SGRBs when observed from a certain angle, or at large distances. This insight sent researchers back into archival data, reviewing old gamma-ray events with a fresh perspective, looking for potential misclassified magnetar flares masquerading as distant GRBs. Historically, this revelation changed the cataloging and classification systems in gamma-ray astronomy. Scientists began incorporating more variables, spectral hardness, spatial distribution, decay tail length, into their classification algorithms. The goal: avoid misinterpreting nearby events as cosmological ones, and vice versa. This greater level of discrimination improved our overall understanding of GRBs as a class and refined models of their frequency, energetics, and origin points. Another deeply significant aspect of SGR 1806-20 was its effect on the theoretical models of neutron star interiors. Until that point, much of the internal behavior of neutron stars, especially concerning crustal fractures and magnetic reconnections, remained opaque, largely due to the absence of observable evidence. But the oscillations detected in the X-ray tail of the flare hinted at a seismic event within the star, a literal vibration or quake, caused by the sudden rearrangement of magnetic field lines and the cracking of the star's ultra-dense crust. This insight lent weight to the idea that neutron stars possess complex internal structures and behaviors, governed by physics that stretches the limits of human understanding. The star wasn't just a solid chunk of matter, it was dynamic, restless, and capable of rearranging itself in a heartbeat, unleashing titanic energies in the process. The flare also had a societal and educational impact. SGR 1806-20 entered public consciousness, not just as a curiosity, but as a stark reminder of cosmic volatility. It became the subject of numerous documentaries, articles, and popular science books. The idea that a star, 50,000 light-years away, could affect Earth's upper atmosphere was both terrifying and awe-inspiring. It reminded the general public, and even the scientific community, of how interconnected we are with the vast machinery of the universe. For many aspiring scientists and astronomers, it was a wake-up call that led them to pursue careers in astrophysics. In the timeline of gamma-ray astronomy, SGR 1806-20's flare stands as a seismic turning point. It redefined what was possible. It reclassified the roles of magnetars. It recalibrated our instruments and our assumptions. It showed that Earth, though small and fragile, is still a participant in cosmic events unfolding on incomprehensible scales. And perhaps most importantly, it left us with a lasting question: what else is out there, waiting to flare? This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.